Okay, we'll get started. So last week we talked a lot about massive star explosions, accretion onto supermassive black holes. This week is going to be a lot about what happens when you put radioactive material inside a ball of gas. I will start with the most vanilla types of explosions, which happen to be some of the most common ones, which are thermonuclear supernovae. And tomorrow we'll be talking about the more exotic ones, things like kilonovae and so on. So our first lecture today will be again by Raim, who will be telling us about the physics of thermonuclear supernovae, and later on we'll hear about the observational landscape. Right. Oh, the mic, please.
Good morning, everybody.
Is there a green light? Yeah, there we go. What is the green light?
Green is flashing out of batteries.
Oh, no, you should go on.
Good.
Yes, I think.
Okay. Okay. So I will start with some things we've already seen, I think, in the very first lecture that Brian gave. So we should all know this. There was this equation, the EDT, which I want to discuss a bit. Do you remember this? Who can tell me the equation? Okay, let's start with what are the things. What is this? Which energy?
Total energy in the cell.
Yes, this will be the thermal energy. Okay. And as a function of time, we want to know what is the derivative of this. And this is changing because of several things. What are they? Adiabatic losses, which is this. I'll talk about this a little bit. What else? Radiation, which is diffusion, so loss of energy, which is proportional to the amount of thermal energy you have. And it is being lost at a rate which is the diffusion time, given by the diffusion time. And the topic of today's talk is also heating from radioactive elements that are there, that are decaying. Okay, so let's start with this term just to make sure we are all on the same page. There is a coefficient here. We're doing everything in orders of magnitude way. But there is a coefficient here which is 1. And that 1 is important that it's 1 and not 2 to make the whole evolution different. So I want to go talk about this for a second. Okay. So where did this term come from? It's adiabatic losses. So it's PDV. P. So this is dE. If we want dE over dt, we need this. This is volume, not velocity. Pressure is given by gamma minus 1 times the internal energy, specific internal energy, so internal energy divided by volume. And the V dt is 4 pi r squared times the r dt, which is velocity v. And this we can replace by 4/3 pi r cubed. So things should cancel in here. And we get minus 3 gamma minus 1 E over T. This is the E, and R over V is T. V over R is 1 over T. So you see that the coefficient 1 in here depends on the adiabatic index that we're talking about. This comes to be 1 only for gamma equal 4/3. Which is the case because we're talking about radiation-dominated material. So this is important because it changes the behavior of this thing if this is not the case, if it's matter-dominated. Let's just take the solution of this part of the equation. If we just do the E dt equal minus E over T, what is the solution of this? We're going to solve the whole thing, so you have to be able to solve this. Guess the solution. Let's see, E goes like T was a suggestion. If we take the derivative of this, we get a constant. If we get
like log E goes like minus log T.
yeah, so if we would guess E goes like T, it will be without the minus.
Oh, it's 1/.
1/T is the minus, yeah. So you can do the E over E and the T over T, 2 logs with a minus. So this is E is equal to some constant over T. And just for units wise, it's good to call this constant E naught times T naught. So there's only one constant, but it's nice to break it this way. So the units look okay. So there is some initial energy at some initial time, and it decays from that on as 1/T. This is the meaning of this equation. If this was a different number, for example, if gamma would have been 5/3, so instead of 1 in here, there would be 2, and then it would decay as T squared. So the way that the energy decays in time due to adiabatic losses depends on this coefficient in here, and this coefficient is only appropriate for gamma equal 4/3. You could have gotten this result very simply if you just say that just by assuming that it's a adiabatic expansion of a volume that is extending and the volume increases as T cubed, you would get the same thing without this equation. Okay, what about this term? What do we know about the diffusion time? So this is the first term. Let's talk about the second term for a few minutes. So the diffusion time is given by what?
Squared over
Say that again?
R squared over C times the mean.
R square over C times the mean free path. Or in the bottom here?
Upstairs.
Yeah. So yeah, another way to see it, this would be the time that photons will free flow out of the material involved, and R over lambda is the optical depth. So times tau, that's the same thing. Yes. So if I want to see how this depends on time, R is equal to VT. Over C, and tau is kappa, the opacity times rho times R, which is VT. But rho itself is M over VT cubed. So this was also shown on the first lecture. We see that this is proportional to 1/T. So as the thing expands, even though it is bigger, it's easier for the photons to escape because there is less scattering. They have to wander around less, even though the overall thing is bigger. Again, if we want to write this with a coefficient, and we want to give this thing units of time, so we can say that T diffusion, which I will stress here is a function of time, is equal some constant with units of time. We can call it T. I think in the in your notes it's called T peak, so I'll copy that. Divided by T. So this is just a coefficient that includes everything we have in here. So if I want to see what this is doing, let's do just that. E over T diffusion, but T diffusion is going like 1 over T. That's the only thing I'm using. And the reason we call it this way is because this is usually the peak of this, or might be the time of the peak of the supernova or the duration. So solving this is again in the same method we described before. We can do dE over E equal minus dt times T divided by T peak square. So we have ln E equal minus half T square over T peak square plus a constant. When we exponentiate this, we get some E naught e to the minus half T over T peak square. So basically it means that the energy due to this radiative losses, it decays, but only after a time T peak. Before that, there is very little change. E is equal to E naught. And after that, it's a super exponential decay. It's more than exponential, it's with a square. Okay? In fact, at the same price that we did this, we could have done those two together, combine them. Let's do that. So dE dt equal minus E over T minus E over T peak square times T. We do the same trick again, dE over E equal minus dt over T minus E is gone already, T dt over T peak square, ln E, ln T, have the same thing we had before. We exponentiate everything, and we just get this 1 over T extra. So we have E of T is given by E naught, T over T naught, T naught over T, the same as we had if we took just the first term here, times E to the minus half T over T peak square. Note that we have this half in here. Look in the notes if it's completely consistent. You can either absorb it into the T peak and then it won't appear in here, but then you'll have to change the definition of this to have 2 in here. It's up to you. You can do it this way or the other way. Okay. So up to here, there was no energy input from anything. Now we want to have this energy input, and initially we'll give it some general form, Q of T, whatever it is. How do we solve an equation like this? What's the technique? It's a standard technique. We have this part of the equation is the homogeneous equation, which we managed to solve. This part is non-homogeneous in the sense that it's non-linear in E, the variable we're trying to solve. So the way to solve equations like that is called variation of constants. You have the general solution to this equation, to the homogeneous part. It has a constant. I split the constant here to E naught times T naught, but it's only one constant. Let's call it A. And the variation of constants method just says this A, if you make it as a function of time, you can substitute in this equation and transform the differential equation into an integral. So let's do that. So I'm guessing a solution of the form. Actually, it's not a guess, because whatever E of t is, I can write it as A of t, which I learned from here, divided by t times e to the minus half t over t squared. Right, so it's like a transformation from E of t to A of t. I substitute this in here, in my equation, and what's going to happen? So when I do dE dt, I'm going to have three terms. One, the derivative of A, one, the derivative of this, and one, the derivative of this. But these two derivatives are going to solve this part of the equation, because that's the way I came up with this. So those terms that do not involve A dot, they will cancel with this and with that. Because that thing with a constant A solves this equation without the Q. Therefore, the equation I'm going to get is this with just the derivative of A. Equal whatever is left in this equation, which is this heat input. So now I multiply and I get an equation for A dot. So now I have an integral. So A of t is just equal to the integral. That we can do from 0 to t of q dot, let's say of t prime, times t times e to the plus half t over t peak, well, dt prime. Is it clear? Okay, so what do we learn from this equation? So A gives me this normalization of the energy, and I see how it is growing with time. Actually, if I wrote it this way, from 0 to t, there is some also value of A in principle at time 0, which is the same as this E naught plus T naught. So I can do A naught plus. And the meaning of A naught we already know from before. It's the product of the initial energy and the time where we release that initial energy. So what we see is that this heat source will give a bigger contribution to the energy of the system in a given time t if it was released as late as possible. And this is obvious. Why? Because if it would have been released early, it would have been lost by adiabatic expansion or lost by leakage of the energy by diffusion. So
isn't that going to also change your hydrodynamics? Release of an additional energy source, because
yes,
you are assuming adiabatic expansion this whole time. You're not you're assuming like a
without this,
expansion.
it's a adiabatic expansion, or without this is a adiabatic expansion.
Yeah, no, you're assuming it's homologous, right?
Yes, I'm assuming that.
And once you start injecting energy in the middle, it doesn't have to stay homologous. You could like drive
okay,
shockwaves if you suddenly inject energy.
Yes, so let's listen. Let's discuss that for a second. So if I would write an equation for the kinetic energy, what would it look like?
One-to-one homology.
Yeah, we will discuss the homology, but write it in whatever regime you want. Any of these terms are going to be there?
U over T.
U over T, yeah. With the minus? No, without. So this is what you were referring to. Whatever was lost to adiabatic expansion is actually coming into the kinetic energy. Okay? And these things, they only change the thermal energy. Both the leakage is just a loss of the kinetic energy is not lost by radiation, and the heating does not contribute directly to the kinetic energy. It does in the sense that it changes E, as we found in here. And therefore, in due time, it may change the kinetic energy. However, in the cases, let's say in type 1a supernova, what is the energy budget that we have? Do you remember the numbers? If you take a solar mass and you fuse it, how much energy is being released? Ten to the 51 Hertz. Yeah. This is relatively small because it's the late stages of the nuclear burning. So if you start from hydrogen and you take a solar mass, you'll get much more than that. But if you just do the late stages starting from carbon and oxygen, you'll only get that. And this is the energy that is initially given only as heat. That energy by this equation is converted to kinetic energy. How quickly? One doubling time of the system, because we know this. The thermal energy decays as 1/T. So you double the time, you double the size of the exploding star. You already have the thermal energy. You give the other half to kinetic energy. So you started with something at rest. It doubles its radius. Already half of the energy is kinetic energy. You multiply the radius by 10. Everything is kinetic energy. This, even the integral of this over time from the radioactive decay is much smaller. Which radioactive decay are we talking about in type 1n supernova? Nickel 56. And that gives much less than this. So it cannot, it increases the energy, but insignificantly. All the energy was released already in the beginning from the thermonuclear reactions, not from the beta decay. The beta decay is a small correction. Why is that therefore important at all? If it's a small correction, because it's being released late. And late is good because of these two factors. So whatever the nickel is giving is not suffering as much from adiabatic expansion and from the diffusion. Okay.
So the issue isn't that it's like, it's not only that it's not a lot, it's also that it's being released when the photons can leak out. Right, so the
yes.
Like
so
you're not.
There are two issues. For the
reshaping
kinetic energy, we're sure that it's not going to matter because it's not a lot. So it can't do anything, even if, no matter when it is released. For the thermal energy, it is the most important thing because the initial stuff, starting from this E naught over E naught times T naught, was already divided by T, even before the radiative losses. So just this, starting from a white dwarf, going all the way to the time where the photons can release themselves, is a huge loss, and nothing is left from this energy, or very little.
And it's deposited roughly like uniformly with mass.
Oh, so this we will discuss how it is. I'll discuss less on how it is distributed in mass. I'll discuss more how it's distributed in time. We'll talk about both. Maybe in the very end, if I have time, we'll talk about distribution in mass. So this is a good point because this is sort of a one-zone model, and in the hands-on, how is it called?
Module.
In the module you'll have later today, there is actually a many-zone model. So I'll try to get there too. Okay. So where are we? So we want to know what is this Q of T. So we can plug it in here and get our energy as a function of time, and therefore the radiation that you will see. If you're asking what is the bolometric luminosity, where is it written in here? It's this one. This is the luminosity. Right, so after you solve this equation, you solve for A of t. A of t times this is E of t. You divide that by T diffusion, you get the luminosity, which is what you may be interested in. Okay, questions up to here? Yes.
It's not T prime and each of them plus T prime squared, right? And or minus
This
T.
is T prime. Yeah.
And the T.
T is only here. Anything else? Okay. So now I want to discuss Q dot. What do we expect of this Q dot? So you already said we're talking about nickel 56 decay.
Sorry, one more question.
Yes.
When did the E turn into plus 1/2?
Where? Here?
Yeah.
When I move this to this side. So if you have something that the homogeneous part of the equation tells you that it decays, then it means that whatever you put initially is less important than whatever you put late. That's why it becomes plus intuitively. Okay, so the nickel 56, what does it do? It decays to what? Thank you. Cobalt 56. And the cobalt then decays to what? Iron. Also 56. What is this? Why are they staying 56? What's going on in here?
Just the neutrons.
Yeah, proton is changing to neutron, so it's not beta decay, it's actually inverse beta decay. So there is a release, I forget exactly the numbers, about 2 MeV here, and I think about 4 MeV here. The rate of this is about 6 days, I think 6 days. And this one is 77 days. So what kind of heating rate as a function of time do I expect from this? If I only had this decaying to that, then the number of nickel atoms, let's call it N1, would be whatever the initial number is, times e to the minus t over tau 1. Let's call this tau 1, and this is tau 2. How many cobalt atoms do I have? So then it's complicated because I did not start with any cobalt atoms. They just got whatever they decayed from the nickel, and then they themselves decay to iron. So I do a differential equation for N2, which is basically N cobalt. So it has a plus N1 divided by tau 1. This is the decay rate of the nickel atoms, and minus the decay rate of themselves, which is on a rate of tau 2. So it's again a differential equation. This is the homogeneous part, N2 and N2. And this is the non-homogeneous part. So we know how to solve this, right? We solve the homogeneous part. The solution for the homogeneous part, everybody knows. It's N2 equals some constant. Like we called it A before, we call it A again. Times e to the minus t over tau 2. But because there is a non-homogeneous part, we'll say this constant is a function of time. We'll substitute this transformation of variables, basically, if you want to think of it this way. In here, when I take the derivative of n2 with respect to time, I will get two terms, one from the A dot, one from this, but the one from this is going to cancel with this because it's solved with this, because that's the solution of the homogeneous equation. And therefore, I'll just get A dot equal to plus A dot times this, e to the minus t over tau 2 equal to plus n1 over tau 1, but n1 I know. Okay, so I move this to the other side. This is where it becomes a plus. And I integrate. So I get that A of t is equal to n1 naught divided by tau 1. This one is e to the minus t over tau 1 plus t over tau 2. Then I have to divide by the coefficient, so maybe there's some other factor here. We can follow this, it's not very important. For now, you'll see why in a second. And then this is A. So if I want to know N2, N2 is just A times e to the minus t over tau 2. This e to the minus t over tau 2 plus a constant. Then what I have left, some constant. This and that cancels for this term, but it remains for this term. So I have e to the minus t over tau 1 minus e to the minus t over tau 2. So it's nice. It's a difference between two exponential, the exponential of the nickel and the exponential of the cobalt itself. And for our case, because tau 2 is longer than tau 1, it's better to write it the other way around with the signs. The signs can be absorbed into the coefficient input. So if you want to know now the heating rate, Q dot, you just have to multiply the number of atoms you have of the nickel as a function of time by the rate of energy emission by nickel, and the number of atoms you have of the cobalt by the rate of energy emission per decay of cobalt. So for the nickel, it will be just an exponential decline. And for the cobalt, it will be a difference between the two because it has to build up itself from the decay of the nickel and then decay by itself. So you see the two coefficients here, I made them equal because I wanted N2 at t equals 0 to be 0. The general solution of this does not have to have these two coefficients the same. But I assume that the starting point of cobalt is 0, so that's why I chose those the same. And in principle, now it's not for this chain, but if this would have decayed to yet another thing, you can just repeat the exercise. So you can write a similar equation. I think it's a cute thing, so if you want, you do it for yourself. You can write a similar equation for N3. It will have a minus N3 over tau 3 and a plus N2 over tau 2. You already know the solution for N2. You repeat the same thing. Okay, why do we have this nickel 56? Let's look at the periodic table or some version of it. So I think you will see this in the module later today, this difference of these two power laws, the rate of cobalt decay. This will be the number of newtons. This will be the number of protons. Where is this guy sitting? Do you know how many neutrons, how many protons it has?
They are not equal.
Hmm?
They are not equal.
Not equal?
Is it 32?
No, they're equal. Here they're not equal. Here they're equal. So let's see what's going on in here. Let's see. There is this line of equality. Who is sitting on this line? Give me elements that you know that are sitting on this line. P equal N. Helium is sitting on the very beginning of this line, while deuterium is sitting just before. But yeah, helium is here. And basically, all the other things that are combination of helium with itself are sitting on this line, because if you combine something which already had equal protons and neutrons, it will remain this way. Where are the stable elements in this diagram?
Close to the line.
Close to the line for low N and P. It goes like this. And as you go higher and higher, you deviate from this line. Why is that the case? What is the structure of this periodic table that we have? So why do things, and actually it ends somewhere, right? It doesn't go to infinity. Who can explain this structure? Of course, it's all very important for our astrophysics stuff. You can just use tables that will tell you what are the things, but maybe you want to get some understanding of this. Yes, so that's part of it. When you put too many protons together, they're unhappy, they repel each other. So why not having, according to this, everything should be here. Just neutrons.
Okay. If you have too many neutrons, then they're going to take that.
Why?
They're not happy, like, if they're just neutrons.
Yeah, but not happy is exactly this question we're trying to understand. So we're trying to understand why are they not happy.
Each successive neutron is more weakly bound.
Yeah. So the problem is when you put too many particles of the same kind together, it's the Pauli exclusion principle that you can apply sort of within the nucleus, and they need to have higher and higher energies. Eventually, that energy is more than the binding energy of the nucleus, and this is why there is an end to the story. This and the Coulomb repulsion. So why is it good at low numbers to put them with the same number? Exactly to avoid this Pauli exclusion principle. So if you put too many neutrons, you better put some of them as protons. They can take lower states. That's why equality is good. When you put too many of them, the Coulomb repulsion becomes to be important, which becomes more important than the Pauli exclusion principle, and you go to this. So where does this story fits in this diagram? We have the nickel 56, which is just helium that went into carbon, that went into oxygen, that came to this nickel 56. So if you burn something very quickly, you fuse some elements very quickly, they will just connect. Then this will decay back towards this value of stability. And this is the stable element. This is the ion 56. So the cobalt is here in the middle, and this is the ion 56. And why am I telling you all this? First, I think it's interesting. But also, we would like to do also the other side of this. So you go along this line when you fuse alpha elements. How do you go to this side? If you have a neutron-rich environment, you have nucleons, you bombard them with fast neutrons. The neutrons come and they join the nucleus, and they take whatever elements you initially had, and they push them as far as they can in this direction. Then what happens? How you let the system relax? Neutrons decay. So now it's the other way. So this was an inverse beta decay. This is now the real beta decay. So you will go this way. And where is this important? Neutron star mergers, macronova, this is it. So in this case, we fused these low elements all the way to the highest element where the binding energy is still favorable of binding more. That's the highest one, and then it decays to the value of stability. Here, you'll have a huge variety of elements, and they will all decay slowly to this. And contrary to what we have seen in here, that we have sum of two exponents, I will try to convince you that in this case, when you mix so many elements and you let them decay, each on its own time scale, and you ask what is the total Q of all this mess, what do you get? Have you seen the macronova power law? Not exponents. So I'll try to explain to you where this power law is coming. What is this power law? How we can roughly understand it. So basically, I'm trying to do, we have already done Q of T for this case. We're trying to do Q of T for all these elements combined, decaying into their lowest energy state over here. Here it's just 1 or 2 beta decays, inverse beta decays. Here there could be many. If the flux of neutrons was high enough, you went far on this and you have a long way to go. So basically you can think about the binding energy per nucleon compared to its value at the value of stability. So by definition, it is 0 in here, and it's the minimum, and it's higher anywhere else. Okay? So now I'm doing nuclear physics in an order of magnitude way. It's going to be very rough. It will give you a good idea of what's going on. So if you think of this as a minimum of energy, and as you go away from it, you get higher and higher energy, then it's likely that the energy as you go away is proportional to the distance from this line squared. This is the way minimums behave, right? There are parabola around the minimal point. So if you ask how many steps your nucleus has from the minimal point, let's call it n, then delta E is likely to be proportional to n squared. And if you ask how much energy is released in each decay, it's basically the derivative of that with respect to n. It's a discrete derivative, but it's not that different. It's proportional to n. So generally speaking, the farther you are from this value of stability, you get more energy per each decay. The closer you are to the value of stability, the decays become less and less energetic. It's more complicated than that. It decays on the spins, it decays on the fine structure of the nucleus. It's complicated, but this is very general. We already see a contradiction of that in here, right? This is farther from the value of stability. This is closer, and yet this has less energy than that. But in general, this is quite good. What is the rate of these decays? Which decays do you think are fast? Which decays are slow? As you go along this line.
The ones that give you the most energy.
Yeah, this is very unstable. It's so far from the stability, it doesn't want to stay there. As soon as the flux of neutrons stops, it all decays, beta decay, beta decay, beta decay, and then becomes slower and slower. Do we know any numbers of beta decay? Do you know any time scale for beta decay?
All of them.
Hmm? All of them?
That's a variety of timescales.
Yeah, we have these. What about neutron?
11 minutes.
Yeah, 11 minutes is the decay of a neutron, just a few minutes. Where is the neutron in this story? It's here, so it's very close. It's one step from the value of stability, which is the proton for the neutron. And the higher ones, they will probably decay faster. It turns out that if there are not some quantum exclusion things, all you care about to know the decay rate is the phase space of the elements into which you decay. The larger the phase space, the more option you have to decay into, the faster the decay will be. So let me write that. What is the decay looking like? Let's say we have some element. Anything, let's say neutron. It decays to what? To a proton. That's it.
No, and electron.
That's an electron, because it has to be a neutron. That's it. Antineutrino. Okay. Who gets all the energy? Well, how is the energy divided by these elements? What kind of...
The proton and the electron get their mass, and the neutrino gets all the extra.
Okay, so very good. The proton and electrons, they have a rest mass. So that's a big fraction of the energy. Even if we go to, if we go higher up in this, it will be a huge thing, the rest mass. And then the rest is all small corrections. So this has a rest mass, this has a huge rest mass, this is a little bit, this is none maybe. So that's a big part of it. Forgetting about the rest mass. Above the rest mass, where is the energy, the thermal energy, which we can now use in these equations? Where is this? Is it the proton taking it, the electron, or the neutrino? So you suggested the neutrino takes it all. Sort of a little bit correct, but not quite. So first year mechanics. If you have two bodies tied with a spring, one is heavy, one is light. You release the spring, they shoot out. Conservation of momentum tells you that the light one is moving fast, the heavy one is moving slow. They have the same momentum. If you want to translate this momentum to energy, p squared over 2m, that means the light one has a lot of energy, the heavy one has very little energy. So this is heavy. It doesn't have energy. It's at least 2,000 times heavier than the other things. So this is no energy, basically. This has some energy, this has some energy. The decay must conserve energy and momentum. So when I'm trying to calculate phase space, I have to do the 3-dimensional, actually it's 9-dimensional integral over all possible momentum. Momentum of the proton, momentum of the electron, momentum of the neutrino. This is all possible phase space, which you can decay into. Careful. out of all these possibilities, I must conserve what? Here I just written any momentum of the proton, any momentum of the electron, any momentum of the neutrino. But there must be a conservation of what? Which conservation laws do we have?
The neutron momentum.
The total momentum. So I need a delta function for P as a vector of the proton, P as a vector of the electron, P as a vector of the electron neutrino. What else?
Energy.
The energy. So the energy is some Q minus the energy of the proton, which is the momentum of the proton squared divided by 2m, momentum of the electron squared divided by 2m of the electron. And what about the neutrino? How do I write the energy of the neutrino? It has no mass. PC. Is this a totally accurate expression or not so good? This term is suspicious.
Depends on whether this is when it's Newtonian.
Yeah, depends how much energy is released. So if the energy released in this decay is whatever is written in here, several MeVs, then these particles, those two, they have several MeVs. So the electron is relativistic. So maybe I should also put this kind of expression for the electron, or I can write the general thing. But I want to keep it simple. So I either assume that the electron is relativistic, or it's completely Newtonian, which is this case. Let's do this case for now. So this could be either that. Let's call it E electron. And it could be either P electron times C, or it could be P electron square over 2m electron. We'll do both cases. So how do I do this 9-dimensional integral? We can do it explicitly, but I want just to know the scaling of it with Q. The only parameter in this integral is Q. The rest are just internal variables of the integral. So there is the simplest way to do it is the following. This is a delta 3-dimensional delta function. So I can cancel any of these. But the best is to cancel this. So to cancel this delta function with this integral. This is just one. And the reason is that I want to cancel this and not the others is that I decided already that this is negligible. So I don't have to worry about what is this doing. Otherwise, I would have to substitute something here. If I want to cancel the others, I'll have to substitute something for those, and I don't want to do that. Okay. And now, if I want to integrate the other things, I will do it very roughly in those two cases. If it's all relativistic, then I have here 6 integrals. Each one of them goes from 0 to Q over C, basically. So I have Q over C to the 6, but the delta function removes one of them, and therefore I have Q to the 5th. It's proportional to Q to the 5th. This is a very famous law in beta decay. So if you go in the relativistic case, if you go and you look up the tables of all the beta decays, you will see that the decay rate is proportional to the Q of that decay to the 5th power. Roughly, there are variations, there are forbidden transitions, so on, but very roughly, this is the case. If you do the Newtonian case for the electron instead, we'll see, depending on time, we'll either do it properly or I'll just write you the answer. So we have here P neutrino cube, that's Q to the cube. And then I have one 3p of the electrons, but the electron now is this. So if this is of order q, p electron is like square root of q. So I have 3 from the neutrino, this one. This gives me 3/2. And then I have to divide by one of the neutrino from the delta function. So this integral becomes proportional to q to the 7/2. There is yet another regime, but I won't go into it. I'll just tell you if you want to think about it yourself. When the decay is has so little energy, it turns out that the attraction between the electron and the proton, or whatever thing is doing the beta decay, is important. You have to take that into account. So this is called the Coulomb regime. And there you get QQ. Okay, so let's just take this now and use and say that the decay rate is just proportional to the amount of phase space we have. And then I can get Q of t and show you that this is a power law. Which power law will depend on which of these regimes I will be in. So it will be a time-dependent power law, meaning not a power law. Where should I do that? Here. So if I want to know the energy injection rate, and let's say I now have all my elements with some energy release of Q. The decay rate is proportional to Q to whatever power that we wrote here. And therefore the time scale which they live is inversely proportional to that. And the idea that I'm trying to use is that 1 over T is equal to the decay rate. Let me explain this. So we started somewhere here. The decay was really fast because Q was large. Far away from the value of stability, Q, this is Q per decay, right? This is Q. Is large if you're far from the value of stability. Therefore, the decay is fast. So if you wait some time, which elements will you find in your system if you started far from the value of stability and you wait some time t? All the elements that are far from the value of stability have already decayed, and the elements you have now are the elements whose decay time scale is t. This is what I'm using in here. And now you ask how much energy they release is Q divided by this t. And here you can choose which of the regimes. Let's do the Q to the 5. So I have Q proportional to t to the minus 1/5. So combining this, I have t to the minus 6/5. This is the relativistic regime. If I do the Newtonian regime, then I'll get, instead of 1/5, 2/7. So I'll get U dot goes like t to the minus 9/7. So this is 1.2, the power law. What is this? This is 1.28. And if I take the Coulomb regime, where the binding energy of the electron, emitted electron and the nucleus is important because the energy is so small, you'll get from the same arguments that it goes like t to the minus 1, and the inverse of that, so 4/3. So basically, here's the result. Q dot as a function of time is t to the minus 1.2 up to some time scale. Which time scale? Then it decays like t to the minus 1.28, and then maybe 4/3. But because these timescales are not so different, we'll discuss them in a second, it's a smooth transition between t to the minus 1.2 to t to the minus 1.33. I want you to tell me this timescale. What defines this? Transition from what to what? Right. So what is the energy release per decay in that transition? Who is doing the transition from relativistic to Newtonian? The electron. What's the rest mass of the electron? Half an MeV. So when the decay is half an MeV, this is when you have this transition. But we know, we got some numbers for decay. We said the neutron decays, and it gives actually a mildly relativistic electrons over a time scale of 11 minutes. So this should be slightly more than 11 minutes. It's roughly 1,000 seconds. This one is roughly 10 to the 6 seconds. Is this clear or is it too much? Questions here?
It's a very nuclear naive question.
Yeah.
Could you explain exactly what's happening in the Coulomb regime again?
The Coulomb regime, the binding energy of the electron to the proton is not negligible compared to this Q. So you want to take that into account. It's a bit more complicated to do, so I won't do it. To understand what is this binding energy, because you need a distance for this binding energy, you can take the de Broglie wavelength of the electron with its energy, say this is the distance of the electron from the nucleus, this is the binding energy, and use this as a correction. Yes?
Yeah, 10 to the 6 feels really long in the context of like a neutron star merger.
Yeah.
So is that more like what's happening, I guess, in the kilonova, like the later time?
Yeah, this is all for the kilonova. Even 10 to the 3 seconds is for the kilonova. So these are the nuclear actions for the kilonova. Yes.
Can you explain again how you counted the power for, like, for instance, Q to the 5?
Yeah, I could have actually done the integral, and maybe I will do it for another calculation. This calculation is so cute, I have to do it. What did I do here? I started with a 9-dimensional phase space. I had the delta function for the momentum that allowed me to cancel the momentum of the proton. And I did that and not the others because this is small and therefore the proton does not appear in the delta function, basically. Then I had 3 powers of the electron momentum and 3 powers of the neutrino momentum. To know what is the scale of each one of them, I compared any of these terms separately to Q. Right, so how big can P neutrino be? The most it can be when this is equal to that and the others are 0. So that gives me a scale for the neutrino momentum. It's just proportional to Q because this is just C. For the electron, it is also proportional to Q if the electron is relativistic, but it's proportional to just square root of Q if the electron is non-relativistic. So this is how I counted it. And I removed one power of the neutrino momentum because of this delta function.
Oh, I think the last part is like, why do you have a 1 more?
So you know when you integrate the delta function, that gives you 1. So one of these 3 momentum is being cancelled by this delta function. You cannot say the same, you can say the same thing about the electron if it's relativistic. If it's non-relativistic, you have to, it's better to cancel the neutrino. Because if you want to cancel the electron, you have to divide it by the derivative of this. Right, you know this, the integral of delta of f of x. Okay, the integral of delta of x dx is 1. This is the cancellation that I'm talking about. If here there is a function of x, then it becomes 1 over the derivative of f at 0. So that's why it's better not to cancel this, but cancel that, which has no derivative, it's 1. Okay.
Maybe that's the intuitive way to think about that, the first cancellation of these, like if you pick the momentum of the neutrino and you pick the momentum of the electron in that 6-dimensional space, that fixes what the momentum of the proton has to be to, so
Exactly.
that means you don't have any choices anymore. So those.
And in the last one, you only have a scalar to fix, because it's a scalar equation, not a vector equation. So it's only one of the 3 variables that is being. So that's why the 9 dimension became 6 because of this, and the 6 becomes 5 because of the other scalar delta function. This is where the q to the 5 is coming from. Okay, so maybe a quick note. I'm debating between 2 things I want to talk about. I'll do this. About the energy distribution between the particles here. We already said something about it. What did we say? Yeah, these have most of it. This, no. What about the division between the 2 of them? It's important for us. Why? This is what we're using. This goes away. This is not ours to use. This is for Kamiokanda. For the macronova, we want, not even, okay. We want this one. So I want to know, out of this Q, this doesn't take anything, good. But these 2, how do they split the energy between them? So it's again, the same phase space argument. So the probability for any momentum of each one of them is according to this. You have to count all the options that satisfy this conservation law. So it could be done in 2 regimes. In the relativistic regime, where the electron is relativistic, what would be the answer? We don't have to do any calculation to get this answer. Equal. Because the electron is relativistic, the neutrino is relativistic, there's no difference between them. You just count phase space, so it's half. So I won't do this calculation. But I will do the one where the electron is non-relativistic. So I want to know what is the average electron energy. So the electron energy is not uniform. Each decay, there will be a different division between how much the neutrino took and how much the electron took. The neutrino can take anything from 0 to, no, everything. Can take everything, then the electron will be at rest. Very unlikely because it's a very small phase space for the electron. The electron can also take everything. And the neutrino will be with no energy. Also very unlikely because it's very low. So therefore the distribution of energies for the electron will be this, and I'm trying to calculate the average. So this is here 0 and Q, and there is some distribution. So all the options are all the decays that are written in here. We already did that cancellation. So we have the 3-dimensional integral of the electron. neutrino and the delta function. So I'm doing the non-relativistic case. Why? Because the relativistic is easy. What's the answer? Half Q. So I don't want to get half Q, that's already known. So these are all the possible decays. These are all the possible decays. What I've written here is 1. But if I want the average energy, I should multiply here by the energy of the electron, which is P squared over 2me. So this is the average energy of the electron. These are all the possible decays the electrons can have. Here I counted them. The electron and neutrino can have. And here are the sum of all the possible decays, each one multiplied by the electron energy. That will give me the average energy of the electron. So the Q and the rest mass of the electron and all that stuff, they will cancel out from the top and the bottom. So I'll go to some dimensionless variables. I will replace this by 4 pi p electron squared dp electron and 4 pi p neutrino squared dp neutrino. The 4 pi's will cancel top and bottom. And here I can solve for what is the magnitude of the neutrino momentum from this delta function. Okay, so what do I have? On the top, I have p electron square, p neutrino square, but there is a delta function here that tells me that tells me what the value of p neutrino is. It's q minus p electron square over 2m. So this is p electron square, p neutrino square, dp neutrino went away with the delta function, dp electron is still here. Oh, and I forgot the energy. P electron square over 2m electron. And on the bottom, I have the same thing. dpe, dpe. Okay? And then I go to this, I renormalize the unit so I don't have to carry these q's and the me. So I call the new variable, which is p electron x. And on the top, I have the integral of, this is x squared. This is 1 minus x squared squared. And this is another x squared. So this is just x to the 4 dx. And on the bottom, I have the same thing, but with an x squared in here. It's a trivial integral from 0 to 1. This 0 to 1 basically saying that the momentum of the electron can go from 0 to q, q over c. So we can do this in 1 minute. So if we open this, I get 3 terms. X to the 4, the integral of that is what? Yeah, between 0 and 1. What is it? It's not 1, you forgot the coefficient. 1/5. Right, the integral of x to the 4 dx is x to the 5 over 5. So between 0 and 1, this is 1/5. The mixed term has x to the 6 with a 2. It has a minus. And from the integral, it's a 7th. And x to the 4, 8, 9, plus 1, 9, I think. Okay? What about this one? Same thing. So this will give us 1/3, right? X squared, integral 1/3, minus 2/5, plus 1/7. This whole thing is what? 1/3. I told you it's cute. It's cute for me. So that means that the electron, because it's non-relativistic, does not share equally the energy with the neutrino. It takes 1/3. If you do the same thing in this Coulomb regime, it becomes to be 1/4. So it actually starts with a half, relativistic case. Let me write that down, because that's our final result. So the average of the electron energy is equal to Q times either a half, if Q is much bigger than an MEV, then the rest M electron C squared, and 1/3 if Q is much smaller than M electron C squared, and 1/2 even later. Quarter, thank you. 1/2 of the original, yes. If you want to think of it as in terms of the useful energy that comes into the macronova, then between this and that, you lost a factor of 2. So from half to a quarter, a factor of 2 over 3 orders of magnitude in time, you can translate that to a correction of the power law. It's about 0.1. So that means that the actual slope is in fact slightly steeper in the transition regime. Okay. Questions? Because I want to completely change the subject. Yes.
So I mean, this is only for free neutron decay, right? Because then you have nucleus decaying, like 30–40% of the energy goes into the daughter nucleus, and that goes into gamma rays.
Okay.
CK.
Only if the daughter nucleus is in an excited state.
Right.
And that gives the gamma ray. Yes. In the kinetic energy of the nucleus, always 0, negligible. 2,000 times smaller than the electron energy.
Okay. In
Okay.
a kilonova, you do have.
But we do have gamma rays, and that is important. Okay, thank you. It's a good point. So it depends on the decay itself. Some decays do decay into an excited state, which then decays by a gamma, and some don't. So when it does decay by a gamma, we have to take that gamma into account as well. And we want to put that into that Q if that gamma can thermalize, and not if it doesn't. It's not always there.
Right, but I mean, in the kilonova, your power law goes as. Oh wait, no, never mind.
These are the power laws
Yeah,
in
yeah.
kilonova. It's not about approximation. So we have, you can look it up, the details of this in a paper by Kenta, Otokezaka. And there are these, more or less, these explanations and comparison to the real calculation done with some starting point of all these elements decaying. There are some simple explanations like this already in early papers by Colgate, maybe some papers by Bryan also. They did a different calculation than what I've done here. I think the paper by Colgate, they assume that there is a population of all these elements, and they took the decay time of each according to the scaling law, but they didn't follow the chain. They assumed that whatever decays is gone. And it's a completely different approach than what I've listed in here, where I assume you started from something, and after a time t, all the elements you have are those that whose decay time is t. It's a different approach. I think this one.
It's two different limits.
I think the other one, if you start far from the value of stability, is not realistic, because you have one decay, they should follow the second decay of the same elements, and they didn't.
No, but the question is whether your energy is dominated by the last decay of elements that started very far from the value of stability, or by the first decay of elements that started like.
But there's no choice here. We know the answer. It's the decay of the elements that started far from the value of stability. First, because most of the elements are here, because they're all bombarded by this high flux of Newton. So they're all pushed here. So most of the elements are here. And as they decay very quickly. So they don't stay here because these are the fast decayers. And at the time t, you'll have all the elements here. And then at a later time, you'll have all the elements here. And only at very late times, you have elements that disappear because they decayed into the value of stability and you can't continue this anymore. But to say from the beginning that they just decay and disappear, it's not
No,
a
but
realistic answer.
it's the ratio. It depends on the ratio of the abundance of those elements relative to the elements that take longer to decay. That's what that's what you want.
But I'm saying that most of it, because you're in a high flux of newtons, you're far from the value of stability. Most of the elements are far from the value of stability, where decay timescales are very short. So you, by definition, start far from it. Okay. Other questions? Questions?
Maybe a comment, but I think you'll know the answer to this. But when I was working on this, at the beginning of kilonova time, I emailed some very prominent nuclear physicists, and they said this process doesn't release energy. I will not name their names. And the idea was when you study stellar evolution, you always learn that it goes up to iron and doesn't go heavier. So they're like, how can you release energy making elements heavier than iron? And I'm wondering if anyone catches the problem with that argument. So how are we able to release energy even though we're starting with elements that are heavier than iron? Anyone see the flaw in the? Anyways, think about it.
So we sort of discussed this.
You first had to give them energy to get them far from the value of stability.
This is the value of stability,
Yeah.
so that's the lowest energy.
Right.
If you're far from it, you will get energy coming out.
But you gave them energy in the neutron capture.
The point is that free neutrons have, there's a lot of, they have a lot of energy potential. Anyways, anyways.
Yeah, you started with neutrons.
Yeah. It's the neutrons that are more weakly bound that give you your energy.
Okay.
Then,
Yeah.
Is there an intuitive way to understand this outer bound of the neutron capture?
This?
Yeah.
Yeah, you need to know the neutron flux.
Yes.
So you have to make a balance between the rate that neutrons come and hit those nucleons and the rate that they decay. So the rate that they decay we did. You have to know the cross-section for absorption of a neutron. You balance them and you get the highest. So the bigger flux you have, this will go farther away. But not much because it goes strongly. The decay rate goes strongly with this Q.
Yes. And this overall shape for given flux that
I don't know.
it doesn't.
So according to this explanation, I think this is roughly constant. But it's not, it does have this shape. I think if I would have been more careful everywhere here, there would be some dependence on the mass of the nucleus, where maybe only in the Coulomb regime, I'm not sure where is the mass of the nucleus coming from. Maybe the absorption cross-section is different. I don't know the answer for this. According to this, if the absorption cross-section would be all similar, they will all go to the same distance from the value of stability, which is therefore this rather than this, but I don't know what gives exactly this banana shape. Okay, I'm a little bit out of time for the last topic, but it is in the module later. So maybe I'll discuss it just briefly. Another chance for a question before I start. So this is about hydrodynamics of the explosion and how to transform this description that we had for multi-zones. You will have multi-zones. I will try to explain a little bit of this in the 5 minutes that I have. So let's say that you have a star. You make an explosion within the star. We have written, I think, in my previous talk, some conservation law like this. The energy of the explosion is rho r cubed in the non-relativistic case, known as the set of Taylor solutions. We've written something like this, which gives the famous scaling that r goes like t to the 2/5. For constant energy, constant density, r goes like t to the 2/5. And actually, if you look at the way an explosion propagates in the middle of the star, this is not a bad description. I have a paper on this. Stars that release some energy in the middle, as the thing propagates in the very center, it goes like this. When this explosion approaches the edge of the star, so what does the density profile looks like? Radius, the radius of the star, 0. The central density basically goes to 0 at the edge. So this description is good for this part, where density is roughly constant. As the shockwave is propagating towards the edge of the star, you would think, and it's correct, that it accelerates. However, the surprising thing is that you cannot use arguments like this to calculate the way that it accelerates. So you could be tempted, if you model the density as a function of the distance from the edge of the star as a power law, which is roughly correct. So rho goes like r minus r, the distance from the edge, to some power, usually called n. You can also fix here the coefficient if you want, because we know the central density. If you want to extend that power law all the way to the center, then you can do this. So at the center, this is 1, and therefore the coefficient is rho c. So close to the edge, you can estimate the mass to be very small. And you can say, oh, maybe you need to put that mass in here and calculate the velocity from that. So it turns out this is the wrong physics. And the reason is that as this shockwave accelerates through this density gradient, it doesn't bring all the energy with it. The shockwave becomes disconnected from the majority of the mass and the majority of the energy that are left behind. So what you have and unfortunately, there's no analytic way to do it. It's sort of a semi-analytic way with solving some ordinary differential equation. but we can't do it here. So I'll just plot to tell you what is the idea of what's going on. So initially you have a shock wave that is running through here, and it indeed spreading its energy over all the mass that it collected. Then it comes here, it becomes weaker because it collected more mass, and so on. When it comes to the edge and starts to accelerate, most of the energy and the mass are being left in the back. And a smaller and smaller fraction of the energy participate in this acceleration. So there is a shock wave accelerating here, but it takes a smaller and smaller fraction of the energy. The bottom result is that the velocity is proportional to the density to the minus, we usually call this number mu. And mu depends on the way the density changes in here, but not very strongly. So if you just remember this, and use mu of 0.2 or 0.23, this depends on gamma, the adiabatic index of the gas, and on this index n of how the power law changes from the edge of the star. This is roughly a correct scaling. So you see it's a very weak acceleration. So now the way to visualize it, if you want to think of it as a multi-zone thing, is to divide the mass of the star counting from the edge inward into shells. Each one, let's say, has double the mass of the previous one, just in your mind. So for each of these shells, they have roughly a constant density in each one. You can calculate the velocity. And then you can treat this explosion as a sum up of many of these shells. Each one of them will have the same equation that we discussed. Maybe with some Q. So each one of them will have its own time where it becomes transparent, where its optical depth is C over V, where the time is equal to the local diffusion time, to the momentarily diffusion time. And this is when the photons from this zone will be emitted, and that is going to be the multi-zone case. How am I doing with time? I'm out. Okay, so this will be just a short introduction to what you will hear more by Annie. Thank you.
Right, so we heard all about how do you solve the problem of having a heating source inside a ball of gas. Turns out that those are some of the most common transients we find in transient surveys. Let's see a show of hands. How many of us care about type 1a supernovae? Yeah, in the here, yeah. Yes, or thermonuclear supernovae, let's say. Okay, yeah, the few. Yes, okay.
Fraught language that you're
Yeah. Okay, or work on, well, I didn't want to say work on because it would mean that you would have to write a paper on that, but care as in like you care about the topic as in it's considered to be important. Yes.
This reminds me of this large built-in quote, ask not what white dwarfs can do for you. You can do it for white dwarfs.
Anyway, so if you take a random transient survey and you just randomly find things in the sky, about 75% of things that you find are going to be type 1a supernovae because they're super bright. So today's talk is going to be about the observations of thermonuclear supernovae, and it will be again by Saurabh. We'll actually be telling us about the stuff he loves doing.
Great, thank you. Thank you. Yes, I'll try and make you care about white dwarf supernovae by the end of the talk. Actually, at the beginning of the first lecture, Kishway said that these were like vanilla transients, and I think he was trying to be insulting, but actually, vanilla was, for a very long time, a very exotic spice from Madagascar, and there were wars fought over it. It is the best ice cream flavor, in my opinion. So I appreciate your compliment there. But yeah, so the talk of thermonuclear supernovae or white dwarf supernovae. And I want to distinguish that in terms of supernovae, right? So we talk about core collapse supernovae, the end of massive star's life. And so we can either talk about the thing that generates the energy, right, the gravitational core collapse, or you can call them massive star supernovae. What is the thing that is exploding? And so on the other side of the fence of supernovae, we have either thermonuclear supernovae, where the ultimate power source that is on the board behind you is the thermonuclear fusion, or we can call them white dwarf supernovae as the thing that explodes. So that, I'm going to use those basically interchangeably today. All right. This is a nice reason to care about them. You have these beautiful images from the JWST. The people who took this image cared about that beautiful galaxy there, but it turns out that there was a type 1a supernova in that galaxy during their image. And in fact, it was one that we observed with JWST. So I'm going to try and go on a little journey in the talk today. I tried to structure it, but it is somewhat unstructured. We're going to end with like what JWST has been teaching us about white dwarf supernovae, and I'm going to focus the talk on the progenitors and explosions of white dwarf supernovae. But I'm going to start a little bit with cosmology. Okay, so you're going to get a copy of the slide. So I listed a bunch of really nice review articles over the past several years that you can look at if you're interested in learning about more. I won't be able to there's whole conferences about what I'm going to talk about, so I won't be able to get to everything. Okay, I showed this before, but just as a reminder, we have these types of supernovae, and there's observational classification. So on the first day of the summer school, I talked about spectra. We use the spectra to classify things, other properties of the supernovae. But in terms of the theory, right, so we have the white dwarf supernovae over here, which are basically just the 1As and their cousins that I'll talk about. And then everything else would be under this massive star core collapse supernova umbrella. Okay, so we're going to focus on this today. Okay, and as a reminder from that spectroscopy lecture, so here's the spectral classification. The 1As at kind of near peak light show elements of iron group elements, and then what we call intermediate mass elements, sulfur, silicon, calcium. And we think this is from the fusion of carbon and oxygen from a white dwarf. We look at late times, we see these, remember we talked about the ejecta thin out, you see through the ejecta, you get to this nebular phase, you see these forbidden lines, and you see it's dominated by iron group elements at late times for these white dwarf supernovae. Okay, and then one reason to care about white dwarf supernovae, so I sort of wear two hats in my own research. One is I really like to explore these and understand what's going on, but the thing that pays the bills sometimes is that we use type 1a supernovae for cosmology. Okay, and so just to remind you a little bit, so I'll start with that a little bit. So the way it works, right? You've talked all about surveys and how you find supernovae. Sometimes it looks like this. Actually, back in the day when I started my research career, there weren't all these automated professional surveys. There were amateur astronomers who would go out and look at the night sky, and they knew what galaxies looked like, and they knew when there was something new. And so in fact, this supernova 1998 BU, which was the first one I really studied for as part of my thesis, was discovered by an amateur astronomer in Italy, observing every night that they could, going looking at this galaxy Messier 96. Okay. So then the cosmology part of the talk is going to be interesting because it basically has like no astrophysics in it. Like we do all the cosmology like pretending we don't know anything. And it turns out that works out pretty well. So, how do we actually do this? Well, okay, someone looks at the night sky, they see a new dot. And as Kishloy mentioned, because of the luminosity of type 1a supernovae, when you just do a survey, a flux limited, magnitude limited optical survey, about half or a little bit more than half of the objects you see are these type 1a supernovae. Okay? So how do you know that? Well, you just see this bright dot. So, okay, supernova, there's a galaxy, it's probably a supernova. Go get a spectrum. It looks like this. And again, you don't need to know any of the physics. You don't need to know what any of these lines are. It just becomes a pattern matching task, right? You see this pattern And it turns out that at least half the time, more than half the time, you see this pattern over and over and over and over, right? With different redshifts, maybe some subtle variations, but you see this pattern, and these 1As are very homogeneous. You always see this. You see this, the pattern changes with time in a very consistent way, right? So all you have to do cosmology with these objects is you observe it, you see this pattern. Again, you don't need to know what it is, and you say, okay, I'm going to call that a type 1A supernova. Right? So then you can get a spectrum, you can get a light curve. Turns out the light curves are also very similar to each other, right? You observe one, you observe another, they go up, they go down, they have these characteristic patterns. Okay, so again, you had a whole lecture about the physics of what is making these light curves, two of them, in fact, right? But for the cosmology, you don't need to know that. You just need to know that they go up and down. Okay, and the thing that you do for the cosmology is you just keep observing these. And in the old days, like when I was starting, people had, we had some other way to measure a distance to a galaxy, and we saw another galaxy, let's say, was twice as far as that first galaxy, and we had a type 1A supernova in both of them. Well, it turns out that the type 1A supernova that was twice as far was always about 4 times fainter, right? And when you see this, like, this is a good clue that this object might be a great standard candle for cosmology, right? You just see this empirically. Again, you don't need to know anything about what they are, but just by knowing the relative, the distances and the brightnesses, you can say, oh, the luminosity seems pretty constant for this class of objects. And that's not true for most things in the universe. Their stars have a huge range of luminosity. Galaxies have huge ranges of luminosity. Okay, and so finding something that is both luminous, like a type 1A supernova is, and relatively standard, you say, aha, I'm going to do cosmology with it. I don't need to know any of the details. I'm just going to go with it. Nowadays, actually, it's like basically during the 1990s, 2000s, instead of like having some other way of measuring the distance, what people did was they found more type 1A supernovae further out in the universe in what we call the smooth Hubble flow, where the redshift of the galaxy is the best indicator of the distance. So now you find one of these type 1A supernovae, let's say at redshift 0.03, and you find another one at redshift 0.06. These are all observable things, right? You know it's a type 1A supernova, you observe the light curve, you measure the redshift, and what you always find is that the one at 0.06 is 4 times fainter than the one at 0.03, okay? So you don't need to know anything about what the explosion is. You don't need to even know the absolute luminosity of any of these explosions. Just from that relative information that these are good standard candles, you can do a lot of cosmology. And in fact, most of the high redshift cosmology is just based on that assumption with some tweaks I'll talk about, okay? So, the cosmological enterprise of using these is very empirically driven and, somewhat astrophysics free, but you can go a long way, Nobel Prizes and stuff with that approach. Okay, so this is one reason why we would want to study these type 1A supernovae. Of course, we also are interested in what they actually are, but this application is quite important. Okay, so the typical challenges, this is a summer school on transients, so you know this. They're rare, they're unpredictable, and they're fleeting. They're not as rare as some of the other transients you've been talking about. They are probably as unpredictable as all the other transients, and they are not actually as fleeting as some, find a kilonova that's gone in 2 days. That's even harder. But these are the challenges that we have. Okay, people took this empirical approach and kept going with it. And so, for example, they measured a bunch of the light curves. They standardized them based on the distance, the redshift of the galaxy, and they made a plot, for instance, of the luminosity in B band or absolute magnitude here versus some other parameter, anything they could find. And this is something called the Phillips relation after Mark Phillips, who actually, with just a small sample, showed this kind of correlation. Actually, it was Mario Hamui who made it with a bigger sample and fixed the slope of the Phillips relationship. And so what you see, the parameter here is something called delta M15. It's the decline rate, how fast the light curve in the B band declines over 15 days. And a typical type 1A supernova, that will be about 1.1. And then it could be a faster decliner or a slower decliner. And if you plot the peak absolute B magnitude, you can see that there's this nice correlation. Okay? And again, totally empirical. You don't need to know what it is. Brian talked about, okay, well, what sets the time scale of the light curve, right? This diffusion time. And so maybe there's a more ejecta mass as we go to the slower decliners, et cetera. Okay, the luminosity is probably set by the nickel mass. But again, you don't need to know that for this plot to be convincing, like, hey, there's a trend here. The scatter in the perpendicular direction is small. I can use this trend to make my standard candle an even better distance indicator. Okay. So that comes the idea that type 1a supernovae are what we call standardizable candles. You use other observable properties, again, not theory, not models, observable properties to make them better distance indicators and continue to do it empirically. Okay. So you see a few things, by the way, in B band, here's the curve, but actually as you go to the infrared, so this is H band at 1.6 microns, this really flattens out. So it turns out type 1a supernovae in the infrared are actually very good standard candles. You don't have to make the corrections that you need to do with optical light curves. So that's something I work on a little bit. Okay, and then how well does this work? Well, you can just use this. If we know that the redshift is proportional to distance in the smooth Hubble flow, so we can plot the redshift on this axis and then the peak apparent magnitude of the supernova on this axis, right? This line is just the inverse square law for light. Twice as far away, 4 times fainter, convert that to magnitudes, you get the slope of this line. Okay? And you can see just by putting points on there, it does pretty well with about 20% luminosity scatter. Okay? If you just treat them as standard candles. If you go further and you use relations like this to standardize the candles, you get something like this. So what you do is you fit the light curve, you measure the light curve parameters, you figure out what the correlation is between the light curve parameter and the luminosity, apply that, okay? And so what you can get is this standardized candle. Can we make that go away? Is that possible? But I don't know how much I'm going to use it, but if not, it's not a big deal. Anyway, underneath there, it says sigma equals 9%. So you go from a 22% distance indicator to a 9%. So that's an improvement by more than a factor of 2. And then, the precision kind of goes as the square of that uncertainty. So it's like having 4 supernovae for every 1 when you apply the standardization laws. Okay, again, completely empirically. So modern versions of this, they use a light curve fitter. I wrote one a long time ago called MLCS2K2. But anyway, in modern times, we use this thing called SALT2. It's a model for the light curves. It has a couple parameters. One is something about that decline rate, which is called X1, and then something about the color of the supernova, that's called C. And then you take the peak magnitude in B band, you multiply by a correction factor based on X1, another correction factor based on the color. Whoever made the model used opposite signs for these, which is like the worst thing, but okay, anyway, it always trips people up. Anyway, you just apply that and then you get this, standardized magnitude. Okay, one really interesting thing is that people often think that it was this Phillips relationship, the idea of like the bright ones and the faint ones, or the slow declining ones and the fast declining ones. By figuring that out, that's what made type 1a supernovae into good distance indicators. And that is somewhat of an exaggerated story. Okay, it turns out there aren't very many of these very fast decliners. And in cosmological samples today, we basically just limit the decline rate to this kind of green shaded region. Okay? And within that green shaded region, it turns out, so that's a kind of range of like this X1, this light curve parameter from about -2 to 2. Okay? X1 is defined to be 0 for the typical object, and it has a standard deviation of ±1. So this is kind of ±2 sigma from the average light curve shape. Okay, so that's usually like the cosmological cuts people use. And then for the color parameter, it's something like -0.1 to 3.3. This is about the B minus V color at peak. Okay? And if you measure what these correlation, the standardization coefficients are, alpha and beta, turns out alpha something like 0.14, beta is about 3. And what you get is, again, it's hidden here, but the color correction beta times C is typically bigger than the alpha X1 correction for modern samples. Okay, and so it's a fact that actually you're correcting the color of the supernova is what dominates the improvement in distances today. Okay, it's not that we don't really use these, so like getting them up to the right place, it's we're trying to standardize the ones in this green region. Turns out the beta times C term. Okay, so the color correction is the largest right now. It's kind of weird, actually. We know some things that will affect the supernova color. So maybe the supernova was just hotter or cooler, so it would be a different color. But we also know that there's interstellar dust along the line of sight, maybe from the host galaxy of the supernova, and that will redden and extinguish the light. What's kind of funny with the SALT2 approach is actually both of those are put into one color parameter. There's no differentiation between intrinsic color differences in the supernovae or the dust. Thank you. So there are other models which try and separate those out and stuff, but it turns out, you're doing everything empirically. You're not putting the physics in, like, oh, dust is different than what the supernova is doing intrinsically. And this model seems to do a pretty good job. When you get to the details, then you start seeing kind of funny things that you might want to do more. But this does really well. Okay, so what can you do that? Well, you,
ask a question. So in the H-band plot where you showed it was very flat. So why is this +10 and the other ones are max?
Oh yeah, this. So first of all, it turns out in the infrared, it peaks slightly early. So to get that peak color, the peak magnitude in the infrared, when this plot was made, there wasn't as much data. But now we have a lot. You could do it at max too. It still works.
So okay, so these are so peak H band magnitudes
in here.
Right. Okay.
But this is, I think you're right that this is at 10 days phase, 10 days after B band max. Right. That's when the H band max was measured. Yeah. Yeah. So you don't have to standardize at the peak. You can pick any other time as well. Yeah. Maybe.
Are there negative consequences to putting that like decline rate cut and stuff like that on your cosmological samples?
Yes, there's negative consequences to everything. It just depends on what level of precision you care about. And so yes, the state of the art today is you try and forward model your whole sample. You whatever cuts you're going to apply, you apply them to your simulated data and see what biases you might be introducing by the cuts you're making. So, that approach works well. You have to be kind of confident that your forward simulation of what your actual data is, has fidelity. But yeah, you can check all of these things. Right. It's not a very restrictive cut. It's ±2 sigma of the, so that you think you're getting most of the objects with that kind of cut. But you could imagine a future where we have so many objects, and in fact, we're writing a paper right now just arguing for this, where you make even more restrictive cuts and you really find very similar objects at different redshifts by making sure that their light curves really match really well. And if you have hundreds of thousands of objects like we'll have with Rubin, that might be an approach to go forward. And then you don't have to make, correlate, like you don't have to correct things. You'll already have everything with the same X1 and the same C. And so it doesn't matter what alpha and beta are. You should, they should work. Okay, so applications. The biggest application from the past was, this stuff that happened in 1998, measurements with high redshift type 1a supernovae. This is a more modern version of that. But then this was, type 1a supernovae we used to discover the accelerating expansion of the universe. So here are the contours from the Riesedahl 1998 paper. You can see that this is shifted relative to a no cosmological constant universe. And so, at that time, there was evidence that, we were an accelerating universe. That evidence has just gotten stronger with time. Okay? And then really, again, interesting thing about this, there's no astrophysics has to go into this measurement. And in fact, you don't even ever have to know what the luminosity of a type 1a supernova is in ergs per second. Because all you need is for this dark energy measurement, you need a differential measurement between relatively low redshift type 1a supernovae, so in the smooth Hubble flow, less than about 0.1, and high redshift. And you're just seeing how much this curve shifts. The low redshift ones set the 0 point, and then you're just seeing how much the curve shifts due to different amounts of dark energy or dark matter in the universe. Okay? So this is why this could be a very empirical kind of thing, and it's it's stood the test of time. People have tried to improve on the empirical methods, but it's actually in the end it's pretty straightforward what you're trying to do. Okay, dark energy, that was exciting. It gets more exciting. So the most recent big surveys is this is from the Dark Energy Survey 5-year analysis. They're starting to see hints, so you can kind of see it here, where so far, for 20, 25 years, the dark energy results from supernovae have been very consistent with a cosmological constant. The vanilla version of what dark energy would be. But maybe it's even more exciting if it's not the cosmological constant, if it's something that's changing with time. And so there's some evidence from supernovae and also from BAO and other measurements recently that suggest that this might be a time-varying dark energy. And so that's really exciting. One reason it's very exciting, especially in the Rubin era, it gives it a target to aim at. For a long time, we were just trying to test this model of lambda, and the theory does not really give you any guidance for how different other scenarios might be, right? Is it different from a lambda at the 10% level, the 1% level, the 10 to the minus 6 level? All of those are very important because it would be not lambda, it would be something dynamical, something more interesting. But without that guide, it's hard to design a survey or an experiment to go for it. Now that we have some indication that maybe it is different at the 10%-ish level, that means that Rubin actually in its first year data will clean up and really test this very well. So we're kind of excited about that. Okay, that's dark energy. Another starring role for type 1a supernovae is the local distance ladder. And here you really do need to know the absolute distance to some supernovae to figure out the expansion rate of the universe, Hubble's constant. Okay.
What is the range of redshift that is best for this?
Sorry, what is the range of redshift for?
That is best. Which supernova do you need?
That's right. So you need ones where you can measure the distance directly somehow, anywhere. So
about the previous,
yeah. Oh, for the previous one. Oh, I see. Oh, yeah. I got your question. Yeah. Yes. For this, where am I? For this time-varying dark energy signal, okay, you can see it's in green here. Okay, and so there's this kind of funny thing happening at the lowest redshifts where the dark energy is changing now. But the problem is the lowest redshifts kind of set your anchor. So it's really, you can move this line around. So it turns out that the biggest deviations between, say, a lambda CDM model, like a flat lambda CDM model, which is purple, you can see that here redshifts 0.2, 0.3, 0.4 are good. Those separate out. And then again here a little bit, and then again kind of here. So actually there are a few, because of this, it accelerates, decelerates, so there's some changes that you actually get a few good redshifts where it's quite different than the lambda prediction. And those are good redshifts both for Rubin here and for Roman at higher redshift. So, that's really nice actually model to aim at, is that the redshifts of the supernovae are places where we are having observatories coming in the near future. Yeah, great. Any more questions with this? Okay, so let me move on to the Hubble constant. So the way to do this is now somehow you need to have one type 1a supernova where you actually know the distance in meters. Okay, and unfortunately or fortunately, I don't know, it depends on your perspective, there was not a type 1a supernova that close to us in the Milky Way where we could have measured that, or get Gaia to measure the parallax of the 1a, we'd be done, but that hasn't happened. There have been 1As in the galaxy. I'll show you some later, but hundreds of years ago. So we're basically limited to type 1a supernovae in relatively nearby galaxies where we have to use some other distance technique other than geometry and parallax to figure out their distances. And so we use a distance ladder. The typical distance ladder today has 3 rungs. One is geometry to calibrate some other astronomical distance indicator. Then you use that to calibrate the 1As. And then you go to the smooth Hubble flow where the motion, the velocity that you measure, the Rashomon velocity, is dominated by the cosmological redshift. And so that's what you need. And so in this example, it's using Cepheid variable stars as that middle rung. There's the famous Henrietta Leavitt law, which says that you can get the luminosity of a Cepheid based on its period. So you use that information. Some people use the tip of the right giant branch instead as an alternate way of using this for this second rung. Okay, so let me focus on the supernova part. You have the second rung where you've calibrated the supernova distances by some other technique, and then you have the ones in the Hubble flow. And when you put this all together, this is from the Shoes team, you get a very precise estimate of what the Hubble constant is, something like 73 plus or minus 1, and there's even some more recent compilations since then. Okay. And the reason this is interesting, and again, talking about cosmology paying the bills for what we really care about, which is the astrophysics of white dwarf supernovae. Of course, this is interesting because there's this Hubble tension between the estimate from the early universe, assuming lambda CDM. So you measure the cosmic microwave background, you assume lambda CDM is the right model for the universe, you predict what the Hubble constant today should be from that, and you get 67.4 plus or minus 0.5, exquisitely measured, okay, or inferred. And then you compare it with the actual observations, and they disagree by some amount of sigma. People debate whether it's 3 sigma or 4 sigma or 5 sigma. So there's a lot of discussion about this, but it seems like a real issue. Newspapers write articles about it. Okay,
And it turns out it's not just one team's analysis, or it's not even just the supernovae. You can do the analysis many different ways. And most indications from the late universe try to measure the expansion rate locally directly are different than what the prediction of the CMB plus lambda CDM. Okay? So the exciting prospect there is that this lambda CDM assumption, where we don't know what lambda is, we don't know what dark matter is, we don't know if it's cold, you know, all those letters, we don't actually know what we're talking about when we write the standard lambda CDM model. So the hope is that actually it's more exciting than this. And so by taking the Planck data and then the correct cosmology, you would get these into agreement. So if this is, you know, can really be confirmed as a real discrepancy between the Planck measurements prediction and the late universe, that would say, oh, the universe, the cosmology is more interesting. And so of course, that's why people are really excited about this. Okay. So let me just say, you know, one of the things is like, yeah, go ahead.
So many times, especially in observational papers, we have to indicate which cosmology we're using.
Yeah.
And everyone is using something slightly different, not always like optimized.
Yeah.
What's your recommendation?
Yeah, I mean, I probably use like H naught of 70. So, you know, back in the day when I was in grad school, right, there was still a debate between 50 and 100. And so 70 was a good compromise number. I have papers which say 65. Anyway, the things have changed in terms of the calibration. Yeah, it doesn't. So the question is, does your application depend on a 5% distance uncertainty or not? Right. So for many of the supernova astrophysics things we're talking about orders of magnitude differences, then probably doesn't really matter. But if it does, then yeah, you should be very precise about what you use. You know, AstroPy has a default. It is the CMB. It is the Planck numbers, right? And if you're measuring things in the local universe, like I'm pretty convinced that that is not the correct expansion rate in the local universe. But you know, we can have this. Okay. And why am I convinced about that? That's this slide. And it's, you know, this is one thing I try in talks, being like, oh, you just saw that we don't know what Type 1a supernovae are. We're going to talk about all these different progenitor scenarios. So how can you be so confident that H naught is 73 plus or minus 1? And it's for exactly the things like I've been saying, that we can do everything on this problem empirically, and we don't need to know what they are to get a precise answer. Okay. And how do we do that? Well, in the Hubble constant measurement, you are comparing Type 1a supernovae that have been calibrated at distances of around, say, up to 40 megaparsecs, so 25, with supernovae that are in the Hubble flow, maybe at 200 megaparsecs. Okay? So unless these two samples are very different, okay, and we have ways of ensuring that they're the same, we can look at the light curve properties, we can look at the spectra, we can look at the host properties. These are all nearby supernovae. Right, we can get a ton of data on both of these sides, right? So unless these are very different, or the universe has changed, the population of Type 1a supernovae has changed over just a few 100 million years, you can correct for any imbalances between these two samples. And as long as those two samples are the same, then you don't have any lever arm for some systematic error to affect this result. Okay? And so a lot of my work has been trying to look at the supernova part of this. Can we break this H naught issue by something in the supernovae? And my conclusion is basically no. Like one way is we did the infrared version instead of the optical. So you still get H naughts in the 70s. We've used, you know, other kinds of supernovae, we different kinds of galaxies, et cetera. We don't get down to 67 doing this. Okay. So my interest is, my work has been on the supernova side. So I don't know, for example, what if there's a problem in the Cepheids part or in the geometry part? Maybe that could be. There are other people who look into that part and they don't think that there's something there. And so it really is like we can be fairly confident in the precision here. Okay, you might argue whether it's plus or minus, you know, 1% or 1.5% or 2%. But you know, I think this is a real issue. And I think there's something, the local universe is expanding faster than we expect. And it's not just a supernova measurement. There's many other ways to get there.
This question. Yeah. So are there Myras and Masers in the Hubble flow detector?
No, those are usually used as calibrators in that second rung. Okay. Yeah. So there is one Maser galaxy that's far. So the best Maser galaxy just happens to be too close. Just like the kilonova 1708-17 was too close, right? We can get a distance to that kilonova. If it was twice as far away, it would be much nicer in the Hubble flow than where it is right now. And so a bunch of the redshift that you measure is some peculiar velocity correction. And that could be 10% error right from that. So no, you cannot push MIRAs out directly to the Hubble flow. Masers, in principle, yes. And the idea was with SKA, like you definitely should be able to, but it turns out they're not very common. And the best, cleanest one, NGC 4258, just happens to be close. And so it'd be great to get a whole bunch more like that. There are about 3 or 4 now, and some of them are in the Hubble flow, and you still get a relatively high H0 with this. Yeah. Okay, I'm going to skip this, but JWST has been contributing to this. There's people write different papers saying, oh, it's less of a problem with JWST, less of attention, more of attention. So I won't go through the details. It really depends on the sample you're looking at. So I'm going to skip this. Okay, but let's start moving a little bit. So now you're trying to measure things, either dark energy to a few percent. Now you want the supernovae to be constant across a lot of redshift. So that could be a problem. Or maybe they're really trying to nail down this Hubble constant thing. So you want to make sure that your supernovae are the same in the 2 samples. Let's start looking at the astrophysics of type 1a supernovae and what they might be related to. Okay. So I'll just touch on a few things, but it turns out the kind of supernova you get depends on the galaxy it's in. Okay. And one example of this is this paper by my recently graduated PhD student, Connor Larison, who looked at different environments for the supernovae. And some of this was known, the cluster stuff was new, but anyway, in the field, if you look at quiescent galaxies, so elliptical galaxies, early type galaxies that are not star forming, and you look at the distribution of the decline rate, the X1, the shape of the light curve, and that has to be something intrinsic to the supernova. It can't be like, dust or anything will not change that shape of the light curve. So you're looking at some intrinsic explosion property of the supernova. And here is the distribution in early type galaxies. It kind of has this perhaps bimodal kind of thing. Whereas if you look at it in star forming galaxies, you see a much different distribution. You see many more slow decliners, and you see faster decliners preferentially in these early type galaxies. Okay. So clearly, we don't think that the supernova looks around and be like, oh, I'm going to look at the galaxy, I'm going to be a fast decliner. There's some physical reason, maybe metallicity. We think maybe age is the key thing, that older type 1a supernovae, ones that take longer from the star formation to explosion, tend to have these faster declining properties, right? But we don't know why that is. Okay? Again, we're still trying to do everything empirically. We'll try and connect to physics a bit later. In Connor's paper, what he showed is like if you actually go to a more extreme environment in the centers of clusters, you can see that this basically these 2 histograms flip. You get almost exclusively these fast declining supernovae in centers of clusters. So this was more evidence that it could be age that is the driver, because these galaxies are among the oldest in the universe. Okay? And this has important implications for, maybe not so much H0, because the age doesn't change over this, in the nearby universe. But when we go to high redshift, right, there are no type 1a supernovae that are 12 giga-years old at redshift 0.5 or at redshift 0.8, right? And so, in fact, one of the conclusions of this paper is if we want to do Rubin type 1a supernova cosmology, you might be best by only using star-forming galaxies at all redshifts, because hopefully the youngest supernovae at any time, the ones that come like 100 million years after star formation, are hopefully more the same at every epoch in the universe. Okay, but that's something we have to test with Rubin, and I think the current data do not do a good enough job of, is dark energy varying? That's why I had a question mark there. It's because these types of corrections are not completely incorporated into the current analysis. It's not going to be an H0 thing. It's not going to solve a 10% H0 issue, but it could be a 1% dark energy issue. Yeah.
How early after star formation can you start getting 1As?
Great question. We don't know the answer to that, right? Like we're still in empirical mode, right? We just see supernovae go off in star-forming galaxies. They seem to go off more often in star-forming galaxies for the same amount of stellar mass. So, okay, so then the question is, okay, you can look at the environment and try and figure out. And what the models say, we have to know what a type 1a supernova is before we can answer this question. But assuming a typical standard model, we'll talk about that, maybe 50 to 100 million years after star formation. And it's different than a core collapse supernova, which can happen, a few to 10 million years after the star formation. So we do think that these are coming from white dwarfs because we do see the distribution of where type 1a supernovae happen is different than where core collapse supernovae happen. And so, yeah, but, again, it's like that once you start bringing a lot of theory priors into this, it becomes, Like if you really believe, and this is like my research career, like people believe they knew that type 1a supernovae were these Chandrasekhar mass white dwarfs that exploded with main sequence or red giant companions, putting mass onto them, right? And that really locks you into an answer to your question, how soon can you do it? But, I want to be a little bit agnostic about that issue because, from the observations, we don't know. Let's try and match up what are the ages of the stars around the 1As and stuff like that. And that gives you a different, kind of number.
It's probably also galactic archaeology constraints.
Yeah, so there's many avenues that people have attacked this. No one has found any evidence that type 1a supernovae are happening within just a few million years of star formation. So it really does push you to white dwarfs on the longer time scales. But the fastest it could be, is it 20 million years, 50, 100? I think that's a little bit uncertain. We do know we find type 1a supernovae in galaxies where there hasn't been star formation for giga years at least, right? And we don't find core collapse supernovae generally in that region, right? So it's telling you something, right? Great question. Yeah.
So I know you said you haven't started looking at why you get these different decline rates yet in terms of the physics.
In the talk, I haven't. I mean,
Okay,
people
yeah.
work on it a lot,
Yeah.
but I'm just trying to go this empirical to physics. That's the structure of the talk.
Right. So maybe you won't answer this question, but I was just wondering, what are the ideas out there for why, age might have an effect on?
Yeah, I don't think there's a really good idea for why age would lead to a faster declining. So remember Brian's lecture, right? Faster declining. It's also lower luminosity, so less nickel and less ejecta mass. What is it about longer lived progenitor systems of 1As that might lead to less nickel production and lower ejecta mass? I don't know the answer, right? If you said they were all Chandrasekhar mass, you should never have a lower ejecta mass, right? So that's a problem, right? Yeah. So it could be something complicated, it could be something simple, but I don't. Metallicity has been another one. There you can say, oh, if you have more neutron-rich elements, it goes back to Rem's nuclear physics. More neutron-rich elements, you can just directly fuse to stable elements, make less nickel 56. So higher metallicity might lead to fainter supernovae that way. That's one idea. But we don't seem to see the right trends with metallicity. So that's why age seems like better, but we don't have a good explanation. So that's a great paper or a great research topic to figure out why this would happen. Maybe Brian has ideas. All right, let's keep going. So that's kind of like something before standardization, like clearly just in the light curve properties, they're different with different environments. For the cosmology, people care about a lot more. They want to make the standardization as good as possible. So they also look at after you standardize, do you still see these differences? And it turns out yes, a little bit. There's a few % difference in the brightness of type 1a supernovae depending on their environment after standardization. You can measure it a whole bunch of different ways. I won't go into the details. But this is the kind of, again, continual empirical approach. Plot supernova luminosity versus anything you can measure on the x-axis. If you see a trend, you see an offset, whatever, correct for it, keep going, try and make the supernovae better. Okay. And you asked, is this dangerous? To do, maybe, because if you're looking at a whole bunch of redshifts and you're making these empirical cuts without knowing what's going on, you might be doing the wrong thing at the wrong redshifts. Right. Okay. The future is bright, of course. We have Rubin, we'll have Roman. We're going to get lots of more supernovae at redshift for cosmology. So this will be great for a bunch of reasons. But okay, I'm sort of halfway done in my time, so I want to go switch to astrophysics now. Okay, so you've seen this kind of slide before, hopefully, right? But this was the distinction I was making at the beginning between the thermonuclear white dwarf supernovae, like what explodes and how, versus the massive star core collapse supernovae, what explodes and how. All right, so, Ram did this calculation in his talk. So it's a pretty simple one to do. You start with carbon and oxygen, let's say. That's the typical end state for the sun is gonna end up as a carbon oxygen white dwarf. The stars that are close to 6, 7, 8 solar masses might end up as oxygen, neon, magnesium white dwarfs. They seem to do something else if you try and put mass onto them. So we think carbon oxygen white dwarfs are the right answer here, okay? Let's assume that it is a Chandrasekhar mass. Remember, there's a maximum mass to the white, for a white dwarf that Chandrasekhar wrote a long time ago. So let's assume that it's a 1.4 solar mass CO white dwarf. So let's say 50% carbon, 50% oxygen. You can just calculate if you fuse all of that, right, to nickel 56. Okay, so it's 2 carbon plus 2 oxygen will get you to nickel 56. 6 and 8 is 14, double that, 28, that's nickel 56. Okay, so you can calculate what is the energy released. And as Rem said, we're already kind of past most of the energy released on fusion. So it's not that much, but you can calculate that. You have the total mass, you figure out what the energy release is, and you find out that it's 10 to the 51 ergs. Okay. You can also do a pretty simple binding energy calculation for a white dwarf, right? GM squared over R, it's about 10 to the 50 ergs. Okay. That's really interesting. It's actually quite different than the core collapse supernova case, where in the core collapse, you have so much gravitational potential energy you can get out, 10 to the 53 ergs. It like totally unbinds the star, which has like a binding energy of 10 to the 49 ergs. Okay. The big problem here is that when again, Rem talked about this, almost all of that gravitational collapse energy goes into the neutrinos, which then may or may not, depending on who you talk to, help unbind the star. Probably a little bit at least. Okay. So these are quite different, but it turns out that the kinetic energy of the ejected that you get is about 10 to the 51 ergs in both. That's like basically a coincidence, almost. Maybe there's something deeper in there. Now, the other thing is, as Brian said, right, if all of this energy from the explosion happens early, as Rem was showing in the equations, it all happens early, and so all of it would just go to PDV work. It would just go to expand the star. And this was my question at Brian's talk: is like, what if there wasn't anything else? What would that look like? It would just be dark. It would be a dark explosion, right? We would notice the effects later on, right? We would see this material hit other stuff, and so that kinetic energy, eventually would make its way into the interstellar medium. Okay, the nucleosynthesis would eventually, make the elements that we care about. So in fact, like if 1As were just dark, it wouldn't change anything except like the lives of astronomers looking at them. I mean, the universe would basically still look the same. The energetics, the nucleosynthesis would basically be the same, but we just wouldn't see them. Okay, but it is the fact that nickel 56 has this particular decay time. Again, if it was 1,000 times longer, the luminosity would be 1,000 times less. So, all of these things have, it's interesting to think about. Okay, but it's this late deposition of radioactive energy at a time when the light can escape that makes it a bright transient, right? And that's, that's I guess the theme of like the whole summer school. That's an important theme. It depends what is the energy source, when it comes out, how it comes out, to what you see. Okay, so that's the basic understanding. We think it's going to be a white dwarf. What is the evidence? What is the observational evidence that type 1a supernovae are exploding white dwarfs? Right? I said, for the core collapse, we have literal pictures of a massive star, Sandulik -69202, was there in 1986, and then it was not there in 1987. We saw it explode, like before and after. We do not have such a picture for a 1a. So, what is the evidence that an actual white dwarf explodes? It's pretty limited direct evidence. There's sort of two pieces in my mind that are direct evidence. Okay? One is this: people have actually seen the gamma rays. Nickel 56 decays sometimes with gamma rays, and you can look for that gamma rays. This, I think, actually the cobalt line. But anyway, people looked. Okay? You have to have very sensitive gamma ray telescopes in space. Turns out the ones we have are not that sensitive unless the supernova is very close. So a galactic one would be great anytime. This is one from 2014 in a relatively nearby galaxy, about 3 megaparsecs away, M82, and there's this one detection of this cobalt line. Okay, there's some weird things about it. It happened kind of earlier than expected, and so anyway, you can read this paper. It's interesting. We can't figure it out, but basically it says that this picture of nickel to cobalt to iron decay should be happening. We're directly seeing the gamma rays sometime. Another thing is this. So usually when you have some kind of explosion in a star, there will be a shock breakout from the surface. So for massive stars, core collapse supernovae and big red supergiants, we can see this. Usually takes some time, and presumably you've talked about shock breakout, right? So it may take a day or two for the explosion to go through the star, and then you see this big UV flash, X-rays from the shock breakout. That's exciting. So you can try and observe type 1a supernovae as early as possible and see and then the luminosity of that shock breakout depends on the size of the star. And when it happens depends on the size of the star. So you could look early enough to see, okay, what was the size of the star? When do you see this kind of flash of the shock breakout? And it's never been seen for a type 1a supernova, but we have, and for 11Fe, we have very good limits, okay? in terms of the light curve of that object was nearby. And so here's the upper limit when the supernova was not detected. Here's when it was detected. Okay, and then you can look at what shock breakout curves might predict. If it was a very big star, you would predict the luminosity would go like that. Here's a solar mass star. Okay, so something like the sun would be like this. And then here's a tenth of a solar mass star, and here's a few hundredths. And you can see this non-detection here is particularly constraining. It basically says that the radius of that star, under certain assumptions, which people have now questioned, and so it's not clear that this still holds up totally, but is something like 1% of the sun's radius. And now we're talking about Earth-sized objects, and that's exactly the typical size of a white dwarf. Okay, so whatever this thing was exploded, it has to have been small. So that basically leaves either a white dwarf or maybe a neutron star exploded. So that could fit this too. We don't know of any physics way to blow up a neutron star. It's so compact already, right? But this really points to white dwarf explosions kind of more directly. Okay. Now, since then, there have been this idea that maybe these 1As have this dark period, in fact, as they expand. And so this analysis did not assume that. This assumed that you would just see the shock right away. So, this is still questionable evidence. So we're talking pretty limited direct evidence, and both of these pieces of evidence have some kind of question marks associated with them. Okay. Am I forgetting anything? Any other signs that these are direct explosions of white dwarfs that people know?
How do we know where t equals 0 is here?
How do we know that way?
How do we know where t equals 0 is?
Oh yeah, so that's basically this question. But people fit the light curve with some usually t-squared rise that says everything is happening very simply early, and that's what this line is just t-squared from the from the later light curve points. Yeah. So and that asymptotes to 0 when you fit that.
Would you say the stronger? I mean, I understand this gamma ray line is the most direct thing, but it's not the highest sigma line I've ever seen. Yeah. so I mean, I guess, but it's pretty convincing evidence in terms of the the decay rate, right?
Yeah.
The late time decay rate.
Yeah, and the overall light curve does behave with that decay rate, right? But there is this thermalization stuff, right? The light curve is not exactly, so you have to put that assumption in. If you really measure the bolometric light curve, yeah, you should see exactly the nickel 56 cobalt 56 decay. But again, that has some kind of thing. Yeah. Okay, so that's, I would say, direct. I would say there's a lot more and quite good indirect evidence for this scenario. One is people take carbon oxygen white dwarf and they blow it up and they look at what it looks like, and it produces the elements, given some tweaks for the model, it looks like what you expect. Okay, and if you blew up a massive star or a neutron star or whatever, you would not get the silicon line and all this other stuff that we see in the spectrum. Okay, so I would say that's pretty good evidence, and you can actually get time series, and you can do that in models, and exploding white dwarfs, whether they're 1 solar mass and you blow them up a certain way, or 1.4 solar masses, you will blow them up in a slightly different way. They kind of match the observations. Okay. We see the 1As are very similar to each other. White dwarfs are all, carbon oxygen white dwarfs pretty much all have the same structure. Right. The bolometric light curves, modulo some assumptions about how much gamma rays escape, follows the nickel 56 decay. And actually the first person to write this down in a paper is actually in a thesis, is Titus Pankey. You should look up this person. He's very interesting life. 1962. Okay. When we look at where these type 1As go off, we don't see any massive star there, unlike core cloud supernova. We look at supernova remnants. I'll show you that. We don't see, some compact leftover object, right? Like a neutron star, a pulsar, or something like that. So again, that would be consistent with a white dwarf exploding. Okay. And then type 1A supernovae occur in both star-forming galaxies and old stellar populations, right? So where, long after star formation, we need some way. And so, having a white dwarf that can live for, a long time, and then having it blow up later, that can work in old stellar population. Okay. So I think, again, there's very significant indirect evidence that we have the right model. Okay. And so then, yeah, go ahead.
So you mentioned this like thermalization a few times. It's kind of like one assumption that goes into this. So I'm just wondering, like, this is a pretty old field with type 1As, right? So like, have people done experiments on like the plasma physics side to
Yeah, that
prove
I
this
don't
better?
know about. I don't know if you can recreate the supernova conditions in any thing. I mean, people, the thermalization rates, and I think this is your module going to talk about this, right? Like they're perfectly reasonable. Like given the model, like yeah, you would predict the gamma rays will leak out at this, like it doesn't have to be very fine tuned for that to work. But we don't have the instruments, right, that collect all the energy to really see the bolometric light curve. It'd be great if we had great gamma ray telescopes and we could just literally add up all the light and see that it is the decay, right? That would be really nice to have. Yeah. But we're pretty sure that's right. Okay, so normally if you go to a conference, especially maybe 15, 20 years ago, this would be the big question. Okay, we know it's a white dwarf, a carbon oxygen white dwarf that explodes. The big question is, what is the companion? Okay, is it a normal star that donates material, or is it another white dwarf? Okay, and so these were the kind of standard pictures. This was the most standard picture. Okay, in fact, the most standard picture is that this companion star should be a red giant, right? Just imagine a binary system. One star has evolved to make a white dwarf. Okay, now you need to create material onto the white dwarf, get it to the Chandrasekhar mass limit, where we think we can assume that an explosion is going to start as the equation of state of the star is changing in the core, et cetera. There's some good reasons to think that once you get stars up to close to that mass, you are primed for an explosion. Okay, so when is their companion star going to start donating material to the white dwarf? Right? When in the stellar evolution of the binary is that going to happen? The most likely time is when the companion star starts to evolve and become bigger. It overflows its Roche lobe and then dumps mass onto the white dwarf, right? So if this was the right picture, the most common thing we should see as the companion to the white dwarf is a red giant. And red giants are bright. So we can go to Tycho supernova remnant and find the red giant and be like, aha, there it is, right? And we have never seen that. We've never seen the red giant. We've never even seen like the stuff around the red giant that should also be there and the material hitting that. So this is a big problem. So some people were like, well, maybe it's not a red giant. Maybe it just happens to be a main sequence star. Like the sun expands about 30% on the main sequence. And maybe it was just tuned just right so that by expanding a little bit, it started being Roche lobe overflowing. That seems already contrived for a main sequence star companion. But that should get below these limits below red giants. Okay? So people thinking about that said, well, I can make a faint star, make it another white dwarf. Okay. Okay, well now, here the thing explodes at 1.4 solar masses, roughly. Here, the masses could be anything. What's going to happen? Is it going to, why should they all be the same when you have two different mass white dwarfs doing something, interacting somehow? And, normally we think about, in this picture, like the two white dwarfs actually collide. That doesn't have to happen. You can get a white dwarf to have Roche lobe overflow, just like you can have, as soon as it gets close enough, one of the lower mass white dwarf is going to be bigger. It can tidally, the material can flow from one white dwarf to the other. It doesn't have to be a direct head-on collision. Though, of course, people make models of that as well. Okay. So it turns out this whole question, this is not the right question. What we know, probably, carbon, oxygen, white dwarf explodes. What we don't know is it really at 1.4 solar masses? We don't know. What is the companion? We don't know. Okay. What is the accreted material? Is it hydrogen rich, helium rich? Is it degenerate material, carbon oxygen? We don't know. Okay. How does the explosion proceed? There's different ways. There's a subsonic deflagration, the supersonic detonation. We don't know this answer. Okay. We have models. A pure detonation of a 1.4 solar mass white dwarf doesn't seem to work. But other than that, there are a lot of options on the table. So is there any interaction signature between the supernova blowing up and this stuff around it? And then what is left behind? Does the whole thing blow up? What if there's two? Did they both blow up? One of them? What? All open questions here. Yeah, question.
You mentioned that neon white dwarfs do something different.
Yeah, we see that the supernova properties for young populations seem to be different. So that's another thing, like how does that fit into any of these? Like how would you solve the progenitor problem by saying, oh, by the way, the young one should explode in a different way than the old ones? Like that's just another thing we don't know, right? Like this is why I like this field. There's, we work on it for decades and we still don't know You can use them for cosmology, but there are all these fundamental questions we don't have answers.
Maybe I can just answer that from the theory side. So if you take a carbon oxygen white dwarf and you increase its mass towards Chandrasekhar, it ignites the carbon at fairly low density. And so it's thought that the thermonuclear burning is able to explode the star. But if you have oxygen neon, it has to get to much higher density before you ignite the oxygen. And by that point, the star is already kind of collapsing. And so it's generally thought that the whole white dwarf will just collapse to a neutron star. So that's from a theory standpoint, it's long been thought, but I don't think anyone has shown definitively that oxygen neons don't explode in their version of single Chandrasekhar scenarios.
Yeah. So sorry, I misunderstood the question.
Yeah.
But yeah. Thanks.
Sorry.
Yeah. All right, and then there are a bunch of observational constraints on this. I'm going through you can look at the rates of 1As. You can look at all these different things. The different models and the different questions from the previous slide predict different things here, and it's still a bit of a mess. That's why I put all those review articles. They talk about every model and its pros and cons. I was organizing a workshop in Munich almost 8 years ago now, and we got all the theorists and observers in a room together, and we were like, okay, let's all the models of 1As that people have, and let's figure out why that model cannot be the dominant channel. And we ended up with an argument against every single model. Okay? And so the conclusion maybe then was like, oh, multiple different channels must contribute to 1As. That's great, but then why do they all look the same? Why are they so exquisitely standardizable? So, big questions. All right, and it's deep connections between white dwarf astrophysics, supernova astrophysics, and then if you care about the distances in cosmology, which I think hopefully in the last few slides I've said you don't need to care about any of that application. This is an interesting problem for like this most common type, at least in a flux limited survey, of explosion, and we just don't know. We don't have good answers to many of these fundamental questions. Okay, so let me just show you some, I'm just going to flash through slides. If there's some topics you're more or less interested in, let me know. This is what when people go look, here's the site of a type 1A supernova. Let's look at pre-explosion observations of that site. Let's see what was there. Okay, so here is an HR diagram with lots of things that could be there. And then these lines are the limits. So nothing has been seen in the site of a type 1A supernova. And so for 11Fe, which is the most constraining, the thing that had to be there has to be down here. Okay, red giants live up here. They're all excluded. I'll talk about helium stars maybe later. Okay, so we're talking about main sequence stars. Here's the main sequence, like low mass main sequence stars. Okay, so the sun would be down here, absolute magnitude +5. Okay, so even a few solar mass main sequence star would be okay, but not really giants. And then white dwarfs would be way down here somewhere. And so, okay, white dwarfs would be fine too. Okay. But no one has seen the red giant that should be the most common thing in that single degenerate standard scenario.
I realized the bottom axis was temperature, ignore me.
Yeah, this is just an HR diagram, yeah. Okay, what if you look after the explosion? So here are a couple examples of we think are pretty clearly 1A explosions. Talk to Armin Rest about how we can measure light echoes from dust that's in front of these, and you can actually see a spectrum of the supernova that happened, hundreds of years ago, and say, aha, it is. I can match it. I can do the pattern matching and say that was a type 1A supernova. So both for Tycho's supernova from 1572 and this one in the LMC G 0509 - 67. There's evidence from light echoes that they were 1As. So those are the ones I show here. And then people look, oh, hey, there are a bunch of stars in the middle there. There's some stars in the middle. Let's go look at that. Well, there are a couple things. First of all, if you are in a binary system with a white dwarf and the white dwarf explodes, that other star should be kind of booking it, okay, away from the center. And so you would want to find a star that's moving quickly, okay? And people look, and it should have interesting properties to be like a donor star. And there's nothing. In both of these cases, there is no red giant with the right properties. There's no even main sequence star. Here, the claim is, people debated, but in this paper, the claim is that the absolute magnitude has to be less than fainter than +8, more than +8. And again, the sun is +5. So even a low, like an M dwarf or a white dwarf are the only possibilities for what's left behind here. Okay. 1572, there was the paper that said this star G was kind of moving kind of fast, and it was kind of interesting. but most recently, most people think that that is not related to this. Okay. Again, the simplest thing would be just see a red giant, like a bright thing. It's not there. So again, it's pushing a lot of people towards these double degenerate scenarios where you have two white dwarfs. Okay, what about the supernova ejecta itself? It should hit the other thing. You know, what do we see there? And so then you look at early times and you try and see, oh, well, you know, so Rem asks, well, how do you know where is time zero? So many supernovae have a very nice, you know, very smooth rise. This is data from Kepler, okay, the space telescope, which observes exoplanets, but sometimes catches supernovae. And you can see, like in this, the orange dots here, that's like a typical one where you just see this very smooth increase and you say, aha, time equals zero was right there. Okay. But then there are a few that have these kind of bumps at early times. Not all of them, but maybe 5–10% of them will have these early time bumps if they're well observed. Okay. And so actually there was a prediction from Dan Kaysen in 2010 is if your companion was a red giant or even a main sequence star, sometimes the ejecta should hit that star, shock it, and produce a bluish bump at early times. And so this might be, you know, this was a prediction and then was actually seen that roughly with the right amount of time. So again, maybe it is the single degenerate, maybe these are running into red giant companions. But then why in the Milky Way or the LMC, we don't actually see the red giants? Big confusion, okay? So another possibility is if somehow the radioactive material gets mixed to the outer layers and you get some of that light to leak early, you can also get these bumps. That also might explain that cobalt gamma ray line that came a little bit too early. So that's another possibility. People talk about what the color of that emission should be compared to a shock bump, which should be hot. I think the jury is still out about what is the source of these bumps. We see them sometimes. You know, the most common thing would be it's material running into the companion. That would be the simplest explanation, but maybe it's more complicated. Okay, early time didn't help so much. What about very late times? Should we see the ejecta hit all the stuff that was around the system? Okay, if it was a red giant or a main sequence star, it should have been hydrogen that's accreting onto the white dwarf. And not all of it is going to fall exactly onto the white dwarf. It should be kind of messy, and so there should be some hydrogen around. You should see the ejecta hit the hydrogen eventually, shock it, and just like, you know, we talked about in massive stars, you should see hydrogen emission at late times. You know, probably narrow hydrogen emission. Okay. And that is seen very, very rarely, not nearly enough to be the solution. So there are some classes where you see some hydrogen material at late times, but I think I can count on, you know, one hand the number of cases that exist. Okay. There are a subset of 1As called 1A CSM where there seems to be a lot of circumstellar material. Again, that's very rare, but that seems to happen. And you know, the question is that like maybe that material is from the donor star, but you know, every so often this binary system will be in a triple. So maybe that material is just from some third star that was nothing to do with the explosion itself. So again, not completely convincing. X-rays, radio, you should see that interaction in other wavelengths. Okay, here's some really nice data which says, you know, here is I'm going to get this. Yeah, okay. Here's what you would predict if the companion was a red giant or a main sequence star or a subgiant. You would predict kind of this amount of circumstellar material that the ejecta should run into. And then here are the limits from the lack of radio or X-ray detection. They look like this. Okay, so maybe in a very rare case you have the right amount from the single degenerate scenario, but most of the time you don't. Okay, again, lots of evidence may be pointing that you have to have two white dwarfs somehow involved.
Can I ask a question?
Yeah.
So in this case, so the mechanism for the stripping is the ejecta hitting the companion and taking along some of its things?
Yes, that can be one, or it could be just material that's left in the system. So it depends. I think for this one, it is stripped from the companion. Here, it may be just circumstellar material from the earlier evolution. I need to go look at the details because it just depends on the kind of radius and time scales. Yeah. Yeah.
I guess there is some problem with Kaysen 2010 model. They discuss something like they overestimate the interaction, the strip hydrogen from the companion star. So probably that the main sequence and red giant is much bigger than the observation data.
You're saying it would be farther to the right?
Yeah.
Yeah. Okay, so then that's even.
There's some overestimate with Kaysen 2010 model.
Okay. I think that, yeah, the Kaysen model is mostly focused on these bumps at early time, and this is generally at late time. So it may be, yeah, we should look into, yeah. But I agree with you that the models are not, incredibly accurately pinned down on this, and then the observations don't seem to match, what the models would say. And the thing is, almost all of this stuff works for core collapse supernovae, right? So people have developed this, for core collapse supernovae, and you do see the X-rays, you do see the radio, you do see, hydrogen, obviously, right? So all the stuff that we think should work, these are methods that are not just people are throwing darts. These are methods that people have, are working for other types of supernovae. Okay, so maybe the simplest thing is it's just two white dwarfs. Why are we fighting about this so much? Okay, there's another kind of interesting paper. This is led by Ken Shen. If it's two white dwarfs and one of them explodes, the white dwarfs, let's say it's still white dwarf mass transfer, so it's still Roche lobe overflow. So the lower mass white dwarf, which is bigger, will transfer mass onto the other white dwarf. That will happen. The white dwarfs are small, so they have to be a lot closer than you would for main sequence stars or other kinds of stars. Okay. And so the orbital speeds for two white dwarfs right before the explosion is going to be way higher. Okay, so if the companion is a helium white dwarf, lower mass, or a carbon oxygen white dwarf, okay, it has to be even closer, right? You can get orbital speeds of in excess of 1,000 kilometers per second. And then let's say the primary explodes, and then the other star is just flung out into space. Okay, so Ken had this great idea that when the first Gaia data release came out, to look for these zooming white dwarfs in the galaxy. Okay, and I like to call them fugitive stars because they are the culprit of the explosion. They are the donors to the white dwarf that exploded, and they are running away from this scene of the crime. Right? So Ken did this analysis for if this method, this is called the D6 model, you can look it up. If this model was the right one for all type 1a supernovae, we should expect to see in that first Gaia data release about 20 such zooming white dwarfs. That was the rough estimate. Okay, and we didn't find 0, we found 3. Okay, so 3 stars where their galactocentric velocities is over 1,000 kilometers per second. And think about it, a star moving at 1,000 kilometers a second, that's free. There's almost no other way to do that other than it had to be in a close white dwarf binary, right? Because if it was a big star, it just will never get close enough to be moving that fast. Okay, it could be 2 neutron stars, but then the gravitational well is so deep there with a neutron star or a black hole. How do you break that? Okay, there is another mechanism with the supermassive black hole at the center of the Milky Way. You can have a binary that gets too close and one star falls in, the other star gets ejected. So that another way you can get very fast speeds. Generally, you don't get up to over 1,000 kilometers per second that way. Okay, so these 1,000 kilometers per second white dwarf looking things, seem to be saying, hey, these are the surviving companions of double degenerate systems. That's the best explanation. There are still some puzzles. The spectra of these, we expected them to be down here in the HR diagram, where white dwarfs are. They are not there. They're way up here in this place where stars really aren't supposed to be. Okay, and so there are many different ways why a star might get there. Merger of 2 other stars, something like that. One idea is that these were white dwarfs, but they were also right next to a big explosion, and you got a bunch of energy that got put into them, and so they get puffed up, and so they get bigger and brighter. And that's just a temporary thing. They'll settle down to become white dwarfs again later. Okay, but this was kind of unexpected where they are in the HR diagram. So again, it's not aha, we found it. It seems like there's no other way to make these fast-moving stars. There weren't enough of them though to explain all 1As, and they seem unusual in this other way.
Yeah. I should know this, but I mean, if they do eventually cool down, then there should be a lot more, I would think, down at the bottom moving fast. Is they just leave the galaxy?
Yeah, so they're on their way out. They leave in a few 100,000 years. But the thing is, if there are more, right? We should have also seen some down here, right? The volume that we could see these obviously is much bigger with Gaia than these, but Ken did the calculation for things down here, we should see 20 of those. So then if the volume is actually much bigger where you could see them, then we should have seen a lot more than 20. So yeah, it's hard to explain. So maybe these make some 1As, but not all. All right, I'm going to switch gears just a little bit and talk about, so we've been talking about vanilla type 1a supernovae. They've been important for cosmology, of course, and we don't know the answers. Turns out maybe we can do a little bit better on other kinds of white dwarf supernovae. So not all white dwarf supernovae are normal type 1a supernovae. This is something that we only kind of really have been learning since the big surveys have been coming over the last 20, 25 years, that there is a whole thermonuclear supernova zoo. So here's the same diagram of decline rate and absolute magnitude, where the Phillips relationship is this kind of gray thing. Turns out there are a bunch of objects that are far away from that. Their spectra look a little bit different. Their Likert properties are different. So not all of them are normal 1As. The vast majority are normal 1As. And that's something that has only become really clear recently. So there's this great ZTF paper by Dimitriadis, which looked at a volume limited sample of exploding white dwarfs. And this plot from Stefan Taubenberger was just trying to highlight all the weird things. So he just put a few normal ones and put a bunch of weird ones on. But this plot from Dimitriadis is actually a volume limited sample. You can get the relative rates of all these weird different things. And what you see in light gray, I mean, they're hidden, like by far the most common thing here is normal type 1a supernovae. Okay? And then there are some of these extremes and fewer of some and more of others. Okay, so you can look at that paper at the relative rates. Okay? But some really quite faint things, some brighter than normal type 1As, some faster declining things, lots of interesting things there. Okay. They have interesting host galaxies. So here are blue star-fringed galaxies at the bottom of each of these slides, red quiescent galaxies. So these different things happen in different things. So for example, these faint low luminosity normal type 1As, 91BG-like or 91T-like, they split. That's what I was talking before. The fast decliners prefer older stellar populations. Again, don't know exactly why, but for the other ones in the zoo, they're there too. That diagram of delta M15 versus absolute magnitude is not the only way to classify them. There are other ways that these white dwarf supernovae separate out. So this is looking at line equivalent widths. So this is a branch diagram. He found that like by plotting these two equivalent widths for two particular spectral lines, it separated the different classes pretty well. Here's another one from Chris Ashall. Just the timing. This is nice because it only depends on photometry. So with a thing like Rubin, we might, where we don't have spectra, we might be able to use this as to figure out what the subtype of each object is. The time of when the supernova peaks in I band versus B band varies as a function of something called the color stretch, how broad the color curve of the light curve is in B minus B. And you can see these different classes separated out there. And this is something you can do with just photometry. So this is kind of nice, promising to figure out what the subclass of these objects are from just photometry. Yeah.
What happened in 1991 that made it suddenly?
1991 was a good year for I was in high school, so I don't know. But yeah, 91T and 91BG, which were kind of the two extremes, happened within a few months of each other. That got prompted the idea of a Phillips relation, which was 1993. That really got the ball rolling. It's actually kind of weird. It's like you thought all 1As were the same, then you find these two weird things, and that actually helps you do use the 1As as standard candles. It's kind of an interesting history. Okay, there are big questions like, okay, there's some like these 91Ts and 91BG, like, are they peculiar? Are they weird? Or are they just the extreme ends of the distribution of normal ones? And this is kind of a semantic question people debate. I think the physics question is it the same progenitor mechanism across those three classes? And some parameter, nickel mass, ejecta mass, whatever, some parameter varies continuously, or are they different things? Okay. So I think open questions, the 91T likes are broader light curves, more luminous. The 91BG likes are narrower light curves, less luminous, different spectral features, et cetera. 91T ones are hotter, 91BG ones are cooler. Okay. One kind of interesting thing is that one way for this double degenerate system to happen is when the material falls onto the white dwarf from the other white dwarf, it doesn't set off the fusion in the center of the primary white dwarf. It actually starts on the edge. And this is called a shell detonation. And for a long time, people thought you needed a lot of material around the star for this to work, to then fuse the carbon in the center. But now, work by Ken Chen, others show that maybe a thin shell of helium fusing on the surface can get the rest of the white dwarf to explode. That's kind of a very promising model. If sometimes you get a thin shell, the idea is like, well, sometimes do you get a lot of helium on the outside that explodes? Do you ever see that? And so had to have Kishale's slide here. And it seems like, yes, in some cases, we do see these thick helium shell detonations. So they are kind of peculiar looking things, but they might say, hey, we have a mechanism that sometimes, explodes white dwarfs this way. Okay, so these are rare, but might be pointing the way. There's another one. These are called super Chandra because using the simple scaling relations that Brian showed you in the light curve. So these are objects which have a pretty high luminosity and a broad light curves. Yeah, you can see compared to the normal. Okay, high luminosity and broad. So that tells you there's a lot of nickel and there should be a lot of ejecta mass. And if you do the calculation, you calculate what is the ejecta mass, it turns out to be more than 1.4 solar masses. Okay, and so these were called super Chandra, and the idea like somehow the white dwarf was more than a Chandrasekhar mass. Like, is that possible? Maybe if it's rotating, you can get something like that, and probably not. And so the actually more likely explanation for these is it's, again, the merger of two relatively massive white dwarfs. That's what gets you all the ejecta mass. That's the kind of leading scenario right now. So lots of different things. All right, I got 15 minutes. Maybe I'll be good. So these are my favorite, these type 1A X's. And the reason I like this one is I said for normal type 1A supernovae, when you look at what was there before, there's nothing. There is one exception for any white dwarf supernova, and it was this kind, a type 1AX, and happens to be a paper that my grad student, Curtis McCulley, led. Okay, and so here was this type 1AX, which is one of these peculiar ones, white dwarf ones, 2012Z. It was in this galaxy, which had already been observed with HST very deep. Actually, it was a Cepheid calibrator galaxy for another type 1A supernova. Anyway, so we had really deep HST observations. And if you zoom in, it doesn't look like much, but there's a smudge right there. And that's where this supernova is. Okay, so that's the first and only time that at the position of a type 1A or type 1A-like supernova, white dwarf supernova, there was something. Okay, we don't really know what that something was. It's pretty hard to measure that exactly. But anyway, it seems consistent. It's quite blue, so that's not a red giant. It's blue. It seems consistent with something called a helium star, which is a regular star where the hydrogen layer has been stripped off and you're down to the helium layer. So kind of an evolved, not quite supermassive, but like, few solar mass star now, where the outer part has been stripped off. And our idea is that that helium star is dumping helium onto a primary carbon oxygen white dwarf. Okay, and this turns out to have a lot of good properties. It turns out you can transfer helium faster onto a CO white dwarf than you can transfer hydrogen because the hydrogen starts fusing and you get novae. The helium needs more energy to fuse, and so it can kind of build up longer. So having a helium star donor is kind of promising. Because it can go faster, it means you can have it younger, and it turns out these type 1AXs favor younger environments. So there are a bunch of things that kind of stick together in these 1AXs. I'll show you where that, let me click. I just want to show you this. So this is the location here of that detection of the 1AX, right? And it's in this helium star kind of region on the HR diagram, okay? Way higher than any of the limits for normal 1As. Okay, so normal 1As don't likely have these bright things, but this 1AX did. So maybe it was telling us the difference. Okay, a lot of interesting things about 1AX is they kind of live for longer than normal 1As. So here's one a couple years after, beautiful galaxies. I want to show the picture, but there is the 1AX, kind of lived longer. One thing we think is happening here is that the white dwarf did not completely explode. And so there was something left behind, an X white dwarf thing, and that's what keeps some energy from escaping, and so you can see it for long. Okay, and it's really interesting. People had such models on their computers. They've tried to blow up white dwarfs. They used something called a deflagration, a subsonic explosion, and what they found is that it didn't always blow up the full star. Okay, and they were like, well, this doesn't look like a type 1A. I'm going to throw it away or keep it in my drawer and not do anything with it. Okay, this is a mistake for the theorists out there. If you can blow something up and it makes something interesting, just because you don't see what it looks like, it's not makes the thing you were trying to make. Doesn't mean it doesn't happen in nature, and probably does happen in nature, and especially with things like Rubin in the future. We're going to see lots of weird transients. So the theorists, the modelers out there, publish everything you find, basically. Unless you've made a mistake. And so, in fact, there was this model with this deflagration, which left a bunch of material in a bound remnant of 1 solar mass. So it started out as 1.4 solar masses, only 0.3 whatever escaped, and the rest was left behind. And it turns out models like this match the properties of 1AXs pretty nicely. In fact, you can tune how much is in the ejecta versus how much is left behind. And that really kind of, can explain the diversity in this particular model. And what's really cool is, I think I showed this in the spectral talk, but we have a huge time series of spectra for these 1AXs, and this kind of model, this pure deflagration model with radiative transfer code, matches over hundreds of days. It matches the observations really well. So we don't know what 1As are, but we might actually start knowing what some of these other ones are better than with normal 1As. And I think for 1AXs, that
I mean, is the parameter the deflagration speed? Is that the thing that
they've been using these models? It's the number of ignition spots, which basically, how much nickel you make and how much energy you put in. But you could imagine, and I don't know when the ignition happened, is you could imagine more, but these models didn't have all that. But. Okay, so here's a kind of an artist's conception of what this kind of system might look like for a 1AX. And what's kind of cool, just like the surviving companions, there have been some detections of these weird, relatively fast-moving stars in our galaxy, not as fast as the other ones, but which look like, hey, this looked like a star that exploded kind of, but it's still there. So you can read these papers. They have these weird abundances that seem like they had carbon nucleosynthesis. And so you get these weird elements, but they're still like white, kind of weird, puffy white dwarfs now. So anyway, these might be the not dead yet surviving companions of partial type 1AX explosions. So kind of neat that those stars are out there. All right, now how much, we got 10 minutes? Okay, we had a bunch of questions. So I feel like maybe I'm not doing, okay. I'm gonna just briefly go through what we've been learning with JWC. This is like my science talk, not a lecture now. So I'm just gonna, but it's so beautiful. Okay, we gotta get the galaxy in the right orientation before we look at it. Let's turn, rotate. Then we can, just like on the movies, we say enhance, and then that's what happens, right? We point JWC at it, we get this beautiful picture. But really, everyone is amazed by the pictures, but the beauty is in the spectra, right? Like that's what I said in the first day. So this is this beautiful JWC spectrum, this unobserved region before. Basically, we had 2 spectra with Spitzer, basically. Now we're getting a whole bunch of these white dwarfs at late times. And what's really exciting, at late times, you get to see through the material. In the mid-infrared, what's good about that is the lines are more separated and we see more elements. So not just iron and cobalt like we see in the optical, we see, nickel, we see intermediate mass elements like argon, neon, other things like that, calcium. And so we can see them. And because we get to just map out the distribution, it's really telling us a lot. Okay. So what are the things that we're learning? And I'll try and be quick. One thing is we see nickel lines at 300 days after max. And on the board back there, nickel 56, 6-day tau, half-life, on that order, okay? So this is many, many taus, many e-folding times later. So this cannot be nickel 56 that we're seeing. So nickel has a stable isotope, nickel 58, and this must be nickel 58 that we're seeing. Okay, so how do you get nickel 58? Now, Rem went over the astrophysics so nicely, right? You're starting with carbon, 6 protons, 6 neutrons. You're starting with oxygen, 8, 8. All the explosive nucleosynthesis happens with the strong nuclear force. No protons turn into neutrons or vice versa during that. So you can only make things with equal numbers. You can only make nickel 56, which should then eventually decay to iron 56. And that's the iron that we see. Okay. But where is all this stable nickel coming from? You must have had some extra neutrons to begin with. So you could say, oh, well, maybe it wasn't just carbon and oxygen. It came from a star where there was probably some heavier elements. You can calculate that. Well, you don't make that much nickel 58 with the extra neutrons. So what's another way? Well, it turns out that if the density of the white dwarf is high enough, instead of inverse beta decay, you can get electron capture, okay? And an electron gets absorbed into the nucleus, merges with a proton to make a neutron. And that can lead to excess neutrons, okay? And that has to happen at a high enough density that the electrons get squeezed into the nuclei, okay? And it turns out the models say that that will happen in massive white dwarfs. Remember, the more massive a white dwarf is, the smaller it is, right? The degeneracy pressure. So that is going to increase the density for massive white dwarfs way over the density for lower mass white dwarfs, okay? Orders of magnitude. And then when you get to this region, you can have electron capture reactions that will make the stable elements nickel 58. This is super interesting because nickel 56 is the thing that powers the light curve. So the more nickel 58 you make, the less, it's not radioactive anymore. So you're actually taking energy away from what could be in the light curve. So you're going to actually make fainter supernovae the more of this you have. Okay. And so it predicts this Chandrasekhar mass model predicts that you will get stable nickel, iron 58, other stable iron group elements with neutron excesses in the centers of these explosions. And it does seem to be what we see. We see these nickel lines with these particular profiles, which suggest that they are at the center. Okay, so strong, stable nickel, that kind of is pointing to our higher mass white dwarf. So maybe they really are all Chandrasekhar mass white dwarfs, which is not what the double degenerate detonation models would predict. They would predict lower masses. So again, we don't know what's going on. Another thing is in the intermediate mass elements, if you look here, here's a really nice example. Here's a nickel line, look at its structure. And I think I showed this on the first day. Here's this argon line, which has this other shape. And I think I definitely showed these movies that Lindsay made. The line shape that you get at these late times, assuming constant emissivity, some other things, it basically tells you the distribution of the ejecta. If you see a flat top like this, it means there's a shell. So the nickel, the stable nickel is in the center. You get that nice rounded thing. But the argon is in a shell around it. Well, where do you get this? You get this when you have a detonation. Okay, you have a supersonic burning front. Why does that happen? So think about an airplane going through the air. If it's moving like a typical airplane subsonically, then that means there are sound waves that are coming from the airplane to the air in front of the plane. And the air in front will know, it will get compressed. It will know, or do something. It will know that something is coming, right? Same thing in the white dwarf. If the burning is moving subsonically, the rest of the white dwarf will adjust. In fact, it will expand because of this pressure wave that's being built up inside. And that will move it to lower density, and you will get a different kind of nucleosynthesis. Okay. In fact, this is actually needed, something called the deflagration detonation transition, to make the Chandrasekhar mass models match observations. But if it's a supersonic thing, detonation, that means the burning front is moving faster than the sound waves can get to it. And so the material that's about to get hit does not know what's coming. Okay. And it can't have changed. It has to be just the way it was before the explosion started. Okay. And so in a white dwarf, what that means is like, well, the density of a white dwarf, it just decreases as you go out. You have basically the same composition, just different densities, and you're just going to explode them, which is this detonation wave going through. What you're going to do is you're going to make some kind of elements in the center, different kind of elements further out. So in the center, you get stable nickel. Further out, you get radioactive nickel. Further out, you don't have, the density is low enough where you don't fuse all the way to what's called nuclear statistical equilibrium. So you get intermediate mass elements. And so you would predict that the intermediate mass elements in a detonation would be in a shell around the center. And in fact, that is what we see. And so that says that somehow a detonation has to be involved. And it could be either in a Chandrasekhar mass white dwarf or in this double detonation scenario with a lower mass white dwarf, but the detonation seems to be indicated. Okay, I don't have enough time, so I'm just going to skip through. We actually looked at one of these super Chandra ones, and we in fact see direct evidence that there were two white dwarfs that merged, and both of them exploded. The evidence is this. Here are the line profiles in different elements. And one of them is offset to the red and one is offset to the blue, and they made different kinds of elements. One made more iron and one made more intermediate mass elements. And we think those are the two explosion sites of the two white dwarfs. Both of them exploded. So it wasn't a double detonation. It was maybe a triple or quadruple detonation where we had multiple explosions from these two things. Okay. There's also a dust continuum. So we think this whole thing was enshrouded in some stuff that was heated up. Anyway, lots of exciting things. I'm going to keep going here. I'm just going to skip to the end. For 1AXs, really cool. So for the 1AXs, the model says that it would be a pure deflagration. It never makes this transition to supersonic. What would be the evidence of that? Well, we shouldn't see any flat top profiles in a 1AX if that was true. Okay, and that was something we knew before we took any JWST observations, that the 1AX model should not show flat top profiles. Okay, the normal 1As show flat top profiles, and then look at the 1AX here. Here's this is a neon line. I forget which. Yeah. Anyway, you can see that these are peaked. There are no flat top profiles to be seen in the 1AX JWST spectrum. Okay, so pure deflagration actually seems like it's the right answer there. Okay, there's unperturbed material. We see some oxygen, which could even match. And there's still a bunch of details. Okay, so I'm going to just skip through this just to get to the end. So we've been taking JWST spectra of a bunch of these different things across the thermonuclear supernova zoo, and we kind of have a story that's emerging. Like we only have one example of this supertron, like where both of the stars explode. The 1AXs seem consistent with a pure deflagration. Normal 1As seem to have some kind of detonation. There has a lot of stable nickel, so that's really pushing towards the more Chandrasekhar mass explosions, which is what we thought, like that should have a normal companion. And it's a little bit strange. It's a quantitative question of how much stable nickel you can get in the double detonation. So maybe it's enough. So I think the jury is still out on that. We would like to get more data. But it's, to me, the really exciting thing is that there's still all these unsolved questions about normal type 1As. We are, JWST is getting us a very nice new view of them. And seemingly, we are starting to understand the ways things are not 1As better than we actually understand 1As. And so hopefully that will help us in the future understand what 1As are. But right now, the picture of the things that we use for cosmology in multiple ways is still quite, exciting to me, let's say, because we don't know what's going on. All right, I'll stop there. Thank you.
All right, I'm sold. I need to start thinking about 1As again.
I need some more vanilla ice.
Yeah, yes, also that. Okay, any questions?
Yeah.
So in this, for this nickel 58, just to confirm, you need this detonation scenario because you need it to remain dense, but nickel 56 is to already have been produced, but it has to be dense in order to get the electron captures, right?
If this electron capture, so there are a few ways you can get the nickel 58. One could be just high metallicity from earlier on. There's this idea of this like neon 22 settling, and maybe you can somehow increase the density of neutron-rich material in the core some other way before the explosion happens. But if this stable nickel is being made in the explosion itself, then, from carbon oxygen, then you have to get that neutron excess somehow. And the most likely thing is, high density burning of, so you get electron captures. And that happens in the central regions of Chandrasekhar mass white dwarfs. The density is just automatically high enough. It can happen in the double detonation scenario a little bit. Like there might be some pockets where some material gets compressed to high density and maybe you can make a little bit of stable nickel that way too. So it's sort of a quantitative question. Like the Chandrasekhar mass models get like 0.1, 0.15 solar masses of stable nickel. And then the double detonation models are like 0.05, 0.0. And the question is whether we always see stable nickel, like it's always there at these times. So it's like, is it always 0.05 or 0.1? We just don't have that quantitative answer yet, but we're working to try and figure that out.
Can I ask one question? So because we've been talking about LSST, as far as, so for most of the events in LSST, they will have to be photometrically classified. And when you get a light curve, you can measure the decline rate fairly well. What you don't know is the luminosity. So if you wanted to do supernova cosmology with LSST events, how do you tell whether something is one of these oddballs or something that's on the...
Yeah, so, I can go back. The oddballs do separate out even in photometric properties. So one thing is, if you start going to farther in the infrared, then it doesn't, they all kind of have the same luminosity, so you start to care less. But yeah, so I was showing this plot on the right here. So this is just based on photometry. It's a color curve, like how much it's stretched on the y-axis, and the timing of the peaks in the x-axis. And you can see the normal ones have this kind of, so the idea is, let's say you only have photometry, you might make a diagram like this and make pretty tight cuts here and say, I'm only going to pick objects in that locus over there. And those are going to be my normal 1As that I would do cosmology for, right? And, you don't have the luminosity, but that's what you're trying to measure, right? You have the redshift, you have to get that somehow. So maybe you can also get that from the light curve in a fit, or hopefully someone will get a spectrum of the host galaxy later for you, or use a photo Z of the host galaxy, right? So then you can put that on your cosmological Hubble diagram.
Okay, any other questions?
Maybe I could ask just a little bit about the nickel formation constraint again. I mean, in terms of some fraction of double degenerates, right? One of the white dwarfs will be pretty high mass, right? So So I guess it's a quantitative question, how many binaries we have where one of the white dwarfs is high enough mass that, if you were to ignite it
Yeah.
From a companion at that mass, it would produce the quantity. So I guess you didn't say much about rates in terms of what we know about binary white dwarfs, but is that sort of a point of tension, that there wouldn't just be enough binary white dwarfs where maybe the companion is...
If that's attention, it's already attention for enough Chandrasekhar mass white dwarf, so it's kind of a problem either way.
I know people have looked at the, under this idea that they need the total sum to be Chandrasekhar, which is not at all obvious.
I don't think that's in the double detonation model. So one of the things, so I mentioned for the Chandrasekhar thing, the most natural way the explosion starts is this deflagration, right? But I showed you that the pure deflagration doesn't explode the whole star always. You don't quite get 10 to the 51 ergs, and the binding energy is 10 to the 50. So you could easily imagine, those are not orders of magnitude apart. So you could imagine pretty weak explosions wouldn't unbind the star, and that's what you actually see. So the explosion for the Chandrasekhar mass model start as a deflagration. Some magic happens, which like in terrestrial experiments, it happens that it turns a deflagration into a detonation. People argue that that magic must happen in white dwarfs, but it's quite tuned when that happens, because if the detonation happens too early, then you just fuse everything to nickel, it becomes too bright. So you need the deflagration to go long enough for the star to expand so that the central density goes from 10 to the 10 grams per cc to 10 to the 7, and then you want the detonation to start, and then that makes a beautiful 1A, right? That's a very contrived kind of model, and it looks like in 1AXs, you don't actually get the transition to detonation, right? Okay, so what's the other way? Well, it turns out, what if you just started with 10 to the 7? Right? What if you just started with a white dwarf that had a central density of 10 to the 7? Well, what kind of white dwarf is that? That is a 1 solar mass white dwarf. I think, did I go too far? No. Sorry, crazy animation. Right, so a 1 solar mass white dwarf is already at the right central density that if you just detonate a 1 solar mass white dwarf, you get a beautiful type 1A supernova, right? So the idea has always been that, sorry, using these crazy terms. There's a keynote way to go to the right slide. I don't know. I never know how to do that. Sorry. I just want to show that Seitenzal plot again. Here we go. Okay. So what you're seeing here is these curves are the 1.4, the Chandrasekhar mass white dwarf, but here's one that's a 1 solar mass white dwarf, and look at its central density. So the idea here is that you would just start a detonation right in the center, and then you would get the right. So in fact, you would want that white dwarf that explodes to be about 1 solar mass, in which case, there are probably a lot more of them, and so that's good. And in fact, there's only a kind of a narrow range between like 0.9, 0.95, and 1.0. That leads to a 1A, and higher mass white dwarfs and lower mass white dwarfs do something else, right? And so the double detonation, the way why they look kind of the same is that you just enforce some narrow range in mass for the primary and just have it completely detonate, and that looks like a 1A.